Welcome to this course on PLC programming using codesys. My name is Marco, I'm an automation engineer from Italy and I will be your teacher for this course. In this course we will learn what a PLC is, how it works, its components and internal mechanisms. We will learn all the definitions and features of the IEC 611313 standard that dictates PLC programming rules internationally. We will learn PLC programming languages and software structures. We will then move on to the codesys development environment, learning all the languages from the standard with a focus on the structured text language. We will learn the basics of programming patterns for automation applications. The course will have a lot of practical examples and exercises. All exercises will have a graphical simulation of an industrial application that will help you understand all the concepts by seeing with your eyes the results of your programming. You don't need to have any previous knowledge to access this course. Some electronics or computer science knowledge might help, but all you need is a technical mentality and the desire to learn. Many companies look for PLC programmers on a daily basis, and this is a career that may lead to many job opportunities. At the end of this course, you will have achieved a good knowledge of PLCs, and you will be able to program them on your own, and make your way into the industrial automation field. What is a PLC? PLC stands for Programmable Logic Controller. A PLC is an industrial computer designed to control industrial processes, such as plant processes, a robot movement, or an automatic machine work cycle. What are the differences between a PLC and a normal personal computer? As you can see, the PLC looks very different from a standard PC. There is no keyboard, no screen, no other devices such as speaker, printer or microphone. This is due to the fact that the PLC purpose is very different from the one of a standard PC. The PLC is placed inside an electrical panel of an industrial machine or plant. It is designed explicitly for its control. It must deliver hardware and software robustness, it has a lot of input-output pins and it is a modular device. But what does control a system mean? It means to modify a system's behavior by acting on some of its physical properties. Whatever is controlling a system is called controller. Let's make an analogy. A person that is driving a car is using all of its tools in order to control the car. The driver is doing the same thing as a controller does. He controls and manages a process. The controller acts on his system using its actuators. The actuators are devices that are able to transform an electrical signal into another physical property, typically a movement. Examples of actuators are electrical motors, pneumatic cylinders, or water pumps. In the car analogy, the driving wheels, the pedals, and the gear stick are the actuators. The controller will also get some feedback from the system using its sensors. The sensors are devices that are able to transform a physical property of the system into an electrical signal. There are many different kinds of sensors: presence sensors, light sensors, temperature sensors, and many others. Even a button can be considered a sensor, as it detects whether or not it is being pressed. In the car analogy, the driver's eyes and ears are the sensors that allow him to get some feedback and information on the surrounding environment. So, a controller will receive data from the sensors and act accordingly, commanding the actuators. In most industrial systems, the controller is in fact a PLC. What is a PLC made of? The core of the PLC is the CPU, the central processing unit, that is actually the brain of the industrial process. The CPU stores the PLC software and reads the values coming from the sensor using input boards and sends command to the actuators using output boards. The union of input and output boards is typically called I/O. Typically, a PLC has also one or more communication boards, or modules, that are used to communicate with external devices, such as an HMI, a human-machine interface, the panel operator used to interact with the machine or process. The PLC may also communicate with many devices that require advanced protocols. This set of devices is typically called field, and the protocol used for the communication is typically called field bus. Now, let's see the origin of the PLC, how they were born, and what changed in the way they are programmed. Many decades ago, the control of industrial systems was carried out assembling panels of relays. Relays are devices that turn on and off. Panels of relays could be used for simple operations, but any modification in the system control logic led to a new panel being assembled. The system had therefore low flexibility, relays would break very often, they were expensive and had low energy efficiency. Panels of relays were replaced by PLC. They are programmable devices and didn't need replacement or redesign for new applications. PLCs needed less space in the electrical cabinet, they were more reliable, modular and flexible. PLCs are programmed using many different programming languages that we will see and learn later on the course. One of these languages is called ladder diagram. This language is based on the same structure of a relay panel, and it is an inheritance of that type of control system. It is a graphical language, and it was very easy to use since many PLC programmers back in the day had an electrical background and not a computer science one. Today, the PLC programming field is catching up with computer science, allowing PLCs to carry out different complex operations and applications with more evolved languages. There is a growing focus on software engineering for PLCs for people with a more academic background. PLC programming skills are very requested by many companies. Wherever you may find an original equipment manufacturer, you may as well find the need of a PLC programmer. In this lesson, we will learn more details about how the PLC CPU works and the importance of its operating system. As we've seen, the CPU is the brain of the PLC, whose purpose is to run the code written by the user to execute all the desired operations. Even a common personal computer has a CPU that runs software and programs, but the purpose is completely different. Now we'll see the difference between a PLC and a PC for what concerns these aspects. A core component of every computer is the operating system, or OS. The operating system is the heart of all the PC software. It manages all the system resources, its devices, it handles process execution and resources allocation, and manages the user interface, or UI. A main role of the OS is to manage process execution and resource allocation. Typically, a standard PC has a single CPU that must run many programs at the same time. Maybe you have opened Google Chrome, PowerPoint, Microsoft Word and Netflix. You also may have a lot of background system processes that are being executed without you noticing. In a Windows OS, you may open the Task Manager to see all the running processes. But how can the OS manage to run all these processes simultaneously if the CPU is able to run only one program at a time? Actually, it doesn't. The OS uses a very clever strategy called round-robin. The round-robin scheduling strategy is about switching the control of the CPU from a process to another so fast that the user will have the illusion that they are all executing simultaneously. For instance, it may execute Chrome for 10 milliseconds, Netflix for 10 milliseconds, PowerPoint for 10 milliseconds, and so on. Since our brain is too slow to perceive 10 milliseconds, we get the illusion that they are all running together, when in fact they are not. In a standard PC, the execution times and order doesn't really matter. If a program is executing for too long, you may experience some slowdown or some temporal freeze of the execution. Now, let's see how a PLC works. A PLC doesn't run on a standard operating system, but instead as a real-time operating system, or RTOS. Real-time doesn't mean very fast. It means that the execution runs within guaranteed time constraints. The PLC operating system has the same functions of a PC one, except for the UI part that is not present on a PLC. The heart of the real-time operating system of the PLC is the process management. In a PLC there are a few processes running that are typically executed with a static priority and known execution times. In a PLC it is extremely important to manage execution times, since a longer than expected program execution may lead to serious damages. In a PLC it is important to manage the task scheduling, that typically is set as cyclical and static, meaning that for each task the programmer must specify the code that is being executed, the cycle time, meaning how often the code must be executed in its entirety, and the priority of the task. Typically, important tasks with high priority will have small cycle times and will be called more often, and less important tasks with low priority will have higher cycle times, meaning that they will be called less often. Typically, as a rule of thumb, priority should be inversely proportional to cycle time. Let's see an example. Let's say we have a machine software with 4 tasks. One task is used for the main machine control. One task is used to handle communication with external devices. One task is used to communicate with an HMI, and one task is used to write data log inside the PLC. In this case, the machine control is the most important task of the system, because it is vital for the whole machine process and therefore should have the highest priority. Then, the second most important may be the communication with external devices. Then the HMI communication, and in the end, the logging is the least important. Therefore, the priorities could be these ones. Then, the cycle times could be the following: 1 millisecond for the machine control, 10 milliseconds for the external device communication, 100 milliseconds for the HMI communication, and 200 milliseconds for logging task. Every process or task will have a cycle time that is being assigned by the user and a computational load that depends on the code that is being executed. It is very important that the computational load time never surpasses the cycle time. If the task execution doesn't respect its cycle time, it may shift the execution of all the following calls. This event is called missed deadline and may cause some serious damage to the plant and people. It is very crucial to manage this correctly. Typically, PLCs have a mechanism called watchdog that in case of instability or too many missed deadlines will stop the PLC CPU and force a reboot in order to ensure the plant's safety. In this lesson we introduced the basic concept of task and process and how it is crucial for the PLC. In the exercises and hands-on lessons we will explore the task concept on the development environment. In this lesson we will talk about the signals that the PLC is able to process and monitor, and we will make an important distinction between analog and digital signals. As we have seen previously, a PLC is made up mainly of the CPU, of the input boards and the output boards. The input boards are meant to read the electrical signals coming from sensors, and the output boards will send electrical signals to actuators. These electrical signals are typically voltage signals expressed in volts. The CPU, being a programmable device, uses data variables to carry out its computation, while sensors and actuators work by using electrical signals. Therefore, a translation level is required, which allows to associate variables with electrical signals and vice versa. The I/O boards carry out this type of conversion. Now we will explore two types of signals, digital signals and analog signals, and we will see how the conversion into variables for both types of signals takes place. Digital signals are signals that can only take two values and are able to express a binary information with only two possibilities. These signals are normally associated with devices that can only have two states. Common notations for these two states are off, on, 0, 1, false, true. The so-called Boolean variable is typically associated with digital signals. Boolean variables, also called bits, are variables that can only have two values, exactly like digital signals. These two values are typically referred as false and true, or 0 and 1. So, typically, an I/O board is able to convert the value of a Boolean variable to a voltage signal and vice versa. An industry standard for digital signals is to use a voltage going from 0 to 24 volts, meaning that at 0 volts voltage is representing an off state and a Boolean variable that has a false value, and a voltage of 24 volts is representing an on state and a Boolean variable with a true value. So, we will have digital inputs that are input signals for the PLC that can be either on or off, which will consist of an input voltage for the digital input board that will be translated into a Boolean variable that will be either true or false according to the voltage value, and this value will be sent to the CPU. Examples of sensors that can be connected to digital inputs are presence sensors, which can detect whether a piece is present or not, or buttons, for instance, which can detect if the button itself is being pressed or not. Digital outputs are instead output signals coming from the PLC, which can be turned on or off. The flow is the following. The CPU will decide a true or false value according to its logic, and the output board will translate this Boolean variable into a voltage to be transmitted to an actuator. Examples of actuators controlled by digital outputs are electrovalves or solenoid valves that can be opened or closed, electromechanical switches that can also be opened or closed as well, and you should know that typically most pneumatic actuators, such as pistons and cylinders, are typically controlled by an electrovalve and therefore by a digital output. Analog signals, on the other hand, are signals that can take any numeric value within a certain range. They are more complex than digital signals as they carry much more detailed information about the physical quantity they represent. These signals are typically associated with numeric variables, and it is the task of the I/O board to convert between voltage and number. A common standard in the industry is to use electrical signals that range from 0 to 10 volts, or also from -10 to +10 volts. The details on how to convert a voltage into a numerical variable with different scales will be explored in one of the next videos on the scaling of analog signals. Therefore, the analog inputs are input signals to the PLC, which can take any value within a range. They are processed by an analog input board, which is responsible to convert the voltage value into a number. Examples of sensors that can be connected to analog inputs are all the sensors that read a physical quantity that can be expressed as a number, such as temperature sensors, current sensors, weight sensors, and many others. Analog outputs work in a similar way. They are signals coming from the PLC, which can take any value within a range. The PLC decides on the basis of its logic the value of the numeric variable, which will be passed to the analog output board that will take care of transforming this number into the corresponding voltage. In this video we have seen different types of signals processed by the PLC. In the practical programming videos we will learn how to use them to write the software and logic of the controller. In this video we will see in detail how to convert an analog value from one scale to another. As we saw in the previous video, a voltage signal is commonly converted into a number by an analog input board, or conversely, a numeric variable is converted into a voltage signal by an analog output board. Generally speaking, we have a starting quantity, represented in blue, that may range between a minimum and a maximum and has a certain value. This quantity must be converted numerically into another scale that ranges between another minimum and another maximum. In this figure, the scaling operations consist in finding the value 2, which represents value 1 in the new scale that ranges from minimum 2 to maximum 2, knowing all the available data. For instance, one could have an analog signal representing a temperature, arriving from a temperature sensor. We know that the voltage varies from 0 to 10 volts, and the value read by the board is 7 volts. We also know that the sensor measures temperature ranging from 10 to 50 degrees Celsius. The question is, what temperature do 7 volts correspond to? To carry out this calculation there is a formula, not too complex, that you see here. In the example above, we can try to make this calculation to find the actual temperature, corresponding to 7 volts. By replacing all the fields and carry out the operation, the result is 38 degrees Celsius. Note that the operation can also be carried out in reverse, simply by exchanging quantity 1 with quantity 2. By performing the inverse calculation, in fact, you get the starting 7 volts. This procedure is particularly useful because very often it happens that the signals are not in the desired scale. Later in the course, we will see how to automate the scaling process with the development of a simple function. Now we will see the details on how to program a PLC and on the standard that dictates the organization of the software within a PLC. Starting from the origins, PLCs have had a different evolution compared to ordinary PCs, since many brands of PLC manufacturers were born and competed with each other, by providing very different systems for what concerns both structures and interface. As a result, each brand used its own systems and created dedicated programming languages for them. So, a multitude of different languages were created, and there was a lot of confusion and difficulty in converting software from one system to another. At some points, the International Electrotechnical Committee issued a standard to unify the software architecture and programming language for PLCs, thus making the PLC systems of different brands more similar to each other, and making so that the software structures and programming languages were the same for all systems. The IEC 611313 standard defines the three fundamental aspects of the PLC software structure. It defines the programming units, the entities that make up the program written by the user. It defines the types of variables, the data on which it is possible to carry out operations within the PLC program, and it defines the programming languages with which it is possible to program a PLC. Now we will see in details these three aspects of the standard, which will be very important for the development of our applications on PLCs. Programming Organization Units, or POUs, are the smallest entities in the PLC software. POUs can be of three types: the programs, the function blocks, and the functions. All programming units, according to the standard, are composed of two parts: the declaration, where all the variables belonging to the programming unit are defined, and the implementation, where the actual programming unit code is written. Now, let's see in details the three programming units of the standard. The program is the main programming unit of the PLC software and is the only unit that can be directly called from a task or a process. As an alternative to scheduling a program within a task, a program can also be called by another program. Each program is unique within the PLC software and cannot be duplicated or instantiated multiple times. The program is an entity with memory. This means that at the end of the execution of a PLC cycle, all its variables remain and will be available for the next cycle. The function block is the programming unit used to guarantee modularity to a PLC program. Like the program, the function block is also an object with memory, with variables that survive at the end of a PLC cycle. The concept of function block is very similar to the concept of class or object that is present in many classical programming languages. The function block is a model used to create different instances of the object itself. Every instance is independent from the other. Each function block instance must be declared to be used, as several copies may exist, and it can be declared or called within other programs or other function blocks. A classic example of a function block is a timer. The timer function blocks refer to its code and its variables defined within the POU. However, several instances of a timer may exist and may be created. For example, a timer for a photocell, a timer for an electrovalve, and one to switch on a generic device. Thus, there will be three different instances of the same function block, each independent from the other, that will act on its variables without being influenced by other instances. Finally, we have the function, which is the simplest object. It is a function that is performed within the PLC cycle in which it is called. It is performed directly and has no memory, so its variables are deallocated once its execution is finished. The concept of function is similar to the concept of procedure that is used in traditional programming languages. Functions can be called and used within any POUs, whether the POU is a program, a function block, or another function. So, a classical POU hierarchy is as follows. There will be tasks that are not programming units, which will be scheduled at certain cycle times. The tasks will cyclically call one or more programs. The programs can call other programs or call other function blocks. Functions can be called from any programming unit. When we will start to see exercises and practical programming, we will see all these concepts in details. Now we will talk about the variables of the IEC 611313 standard. Variables are data containers, located in portion of the controller memory on which various types of operation can be performed. Two very important aspects of the variables specified in the IEC 611313 standard are the visibility, meaning from which point of the various programming units the variables can be read and modified, and the type, meaning the type of data that is represented by the variables. When declaring a variable, it is necessary to specify both the visibility and the type of data described. There are 5 basic types of visibility of a variable that can be specified. There are local variables, indicated by the var symbol, which are part of the POU and can be read or modified only within the POU itself. Other POUs cannot access these variables. There are input variables of a POU, indicated by the var input symbol, and can only be modified from outside the POU, when it is called, and the POU can only read them. There are output variables of the POU, indicated by the var output symbol, which can be modified only from the POU itself, but not from the outside. Then there are the input-output variables of a POU, indicated by the symbol var in-out, which can be exchanged between the POU and the outside and can be modified both from the POU itself and from the outside. Then there are variables that are not part of the declaration of any POU, the global variables, which are declared in dedicated containers and can be read and modified by any POU present in the project. Now, let's look at the types of data represented by variables in the standard. Here you can see 4 macro lists of types of variables: the bit and its extensions, integer numbers, real numbers, and some other additional types of variables. Let's start from the classic most used variables, which we have in part already seen. The Boolean variable. The Boolean variable, as already mentioned, is a variable that can have 2 values, 0 or 1, also called false or true. The Boolean variable occupies a bit in the PLC memory, and it is often called bit. There are also extensions of the Boolean variables, which are groups of bits, such as the byte, which occupies 8 bits and consists of 8 Boolean variables, the word, which is a set of 16 bits, and the double word, which is a set of 32 bits. Now, let's move on to the variables used to represent integer numbers. There are different types of integer variables, and you need to pay attention to certain aspects when choosing the right type of variables. Be careful that the variable can be either signed or unsigned, meaning that it can represent both negative and positive numbers, or only positive numbers. And also, you should look into how much memory the variable occupies. Variables that take up much more memory can represent a bigger range of number, while variables that take up less memory can represent only a smaller range of numbers. Let's look at the int type variable. It is a signed type of variable and it occupies 16 bits. It can be seen that it can represent number ranging from minus 32,767 to plus 32,768. If you need to represent numbers outside this range, you will have to rely on other variables. Here is a list of all types of integer variables allowed by the standard. Starting from the short int, that has only 8 bits to represent numbers, up to the long int, that has 64 bits and can represent gigantic numbers. Typically, the 16 and 32 bits versions are the most used, meaning you will often use the uint, dint, udint, and int variables, since it is rare to use numbers that exceed 1 billion. Then there are variables that are used to represent real numbers or floating point numbers. There is the real variable, which uses 4 bytes or 32 bits for the representation of the number, that in other programming languages is known as float, and the long real number, which uses 8 bytes or 64 bits, that in other languages is known as double. Moving on to other types of variables, we have the string variable, used to represent a short text, and then we have the time variable, which is used to represent a time period. As a notation to assign a value to it, write t hashtag and the time to represent. For instance, t hashtag 5 minutes 10 seconds 450 milliseconds or t hashtag 10 milliseconds. Other less used variables are useful for representing dates and times, such as time of day or date and time. We saw several types of variables in this video. Keep in mind that the most used variables are the Boolean variables, some variations of the integer variables, the real variables, and the time, which we will use in depth in the course. Now, let's see the PLC programming languages defined in the IEC 611313 standard. These languages are dedicated to PLCs and are not used in the world of traditional IT. The standard provides a set of 5 programming languages, including 3 graphical languages and 2 textual languages. Recently, the instruction list language was removed from the standard, leaving only 4 languages in there. We have already briefly talked about the ladder diagram language. Ladder diagram is a graphical language based on the relay logic, which is mentioned in the previous videos. It follows a relay panel assembly design. It is very simple and intuitive for anyone with a minimum electrical knowledge and does not need a great knowledge of computer science to be able to use it. The main downside of this language is that, being so simple, it is not very targeted for complex applications. As soon as you have something a little complex, it becomes really complicated to manage, organize, and read code written in ladder diagram. This language is widely used in small business realities and in the world of process automation. My personal advice and opinion are to use it only for simple functions and limited portions of the PLC software. Another language of the standard is the Functional Block Diagram, or FBD. Another graphical language quite similar to the ladder diagram language, which is based on the assembly of block diagrams in an horizontal lines of codes executed from top to bottom. This language is simple and is particularly useful to visualize block codes in a clear and simple way. As for the ladder diagrams, large products written in FBD become difficult to manage and debug. There is an alternative to the FBD implemented in codesys and other PLC development system that is not officially part of the IEC 611313 standard that is called Continuous Function Chart, or CFC. CFC is a variant of the FBD, in which the blocks are not arranged in horizontal lines but take place on a 2-dimensional screen in a more flexible way. The execution order of the individual blocks is dictated by a number, placed in correspondence with the block. Now, let's see the only textual language of the standard, the structured text. This language is a textual language with lines of code very similar to classical computer programming languages, that has a syntax very similar to Pascal. This language is by far the most powerful and flexible language of the standard. It is easily scalable and usable for complex application. It is compact and, being textual, it is easily portable from one system to another. The only downside is that it can be complicated and difficult to use for those who don't have a computer science knowledge and for those who have a more electrotechnical background. My personal opinion is that the structured text should be used for most PLC programming, particularly for complex projects. So I advise everyone to try to learn structured text, because it will greatly improve programming and debugging efficiency for all your projects. The last language that we will see is the Sequential Function Chart, or SFC, which is a vertical block language with states and transitions. This language is very useful to create state machines. The state machine is a very useful programming pattern to manage sequence of operations that we will see later in the course. The main downside of this language is that with a little knowledge of structured text, it is possible to achieve the same result of SFC with some extra flexibility. In the practical session, we will learn how to use all these languages, exploring the pros and cons of each one with projects, exercises and examples. In this video, we will see what codesys is and why it was chosen for this course to learn how to program PLCs. Codesys is a development environment for PLCs and real-time systems, developed by a company called 3S Software. Codesys allows the user to program many different systems in the languages of IEC 611313 standard. It has a free demo with unlimited duration that has most of the features of the paid versions and provides the user with a very useful simulation mode that can be used for testing PLC programs without the need of a real PLC. Codesys has an excellent online debugging system which is very useful to understand the basics of PLC programming. But why are we using Codesys and not another development environment? There are many PLC brands, and most of them use a proprietary development environment. Therefore, technically, each PLC brand has its own development environment, which should be studied and learned before being able to program PLC of that brand. This is true, but many PLC of different brands are programmed directly using Codesys and support the development environment in its entirety. Furthermore, several of the larger PLC manufacturers have development environments that are based on Codesys. In particular, PLC leading manufacturers such as ABB, Schneider Electric and Beckhoff have a Codesys-based environment. This means that their environment is basically identical to Codesys in terms of structure, interface and use, but it is equipped with special additions to support their devices and their brand. So, being able to use Codesys allows you to know and understand and get to know an environment and a structure shared by many PLC manufacturers. In this video we will explore some very useful and important features of the IEC 611313 languages. All the functionality that we will see in this video are function blocks, which, as we've seen previously, are objects with memory that must be instantiated and integrated into other programming units. These features are present within Codesys libraries, but are also implemented and provided in other PLC programming environments with the same name and functionalities, since these function blocks have practically become standards. These features are divided into edge detectors that allow you to detect when a Boolean variable has changed value, timers to create delays or to wait some specified time or to filter some signals, counters to count certain events, clocks to generate periodic signals. The first block that we will see is the R-trig, the rising edge detector. This block has a single Boolean input called clock and a single Boolean output named Q. Q will always be false unless a rising edge of the clock signal is detected, meaning that a change in value from false to true in clock has been detected. In that case, Q will become true and will stay true for a single PLC cycle. The ftrig function block is a similar block that it is used instead to detect the falling edge of a Boolean variable. It has the same structure as the rtrig, and Q will be true only when a falling edge of the clock input is detected, meaning when the clock will go from a true value to a false value. Now let's move on to timers. The ton or timer on is the most common and used timer. It is a function block with 2 inputs and 2 outputs. In is a Boolean input used to activate and start the timer. PT is a time type input, which is used to specify the timer time. Q is the main Boolean output of the object. Q will remain false and become true if in has remained true for longer than PT. ET, on the other hand, is an accessory output that tells you for how long the in input has been true. ET stands for elapsed time. The result is that once in has been set to true, Q will become true after a delay specified by PT. Setting in to false will reset the timer. The TOFF, or timer off, has a similar functioning. It has the same inputs and outputs as the ton. After having set into false, Q will become false after a delay specified by PT. Setting in to true will reset the timer. The TP, or timer pulse, works very differently. It has the same inputs and outputs as the ton and TOFF, but TP is used to generate pulses on the Q output. After a rising edge at the in input, Q will become true and remain true for the time specified by PT. Now, let's move on to the counters, very useful tools to keep track of how many times a certain event has occurred. The first counter that we will see is the CTU, or counter up, a function block that is used to count only upwards. The counter will show its value on the CV output and increase the value each time a rising edge is detected on the CU input. With the reset input, you can reset the counter value to 0. And if you want, you can specify a numeric value in the PV input so that once the value of the counter has become larger or equal than PV, the Boolean auxiliary output Q will become true. The CTD, or counter down, on the other hand, is a counter used to count exclusively downwards. With a rising edge of the CD input, the counter value will decrease. In the PV input, the starting value of the counter is specified, and by raising the load input, the PV value will be loaded into the counter. There is also an output Q, which will become true when the counter value reaches 0. The last counter that we will see is the CTUD, or counter up-down, which is the union of the CTU and the CTD that allows you to count in both directions. As you can see, it has the union of the input and outputs of the two previous function blocks. Using the CU input, you can increase the counter value, and using the CD input, you can decrease it. With the reset input, you can reset the counter to 0, and with the load input, you can load the desired value specified by the PV input. There are also two auxiliary outputs, QU and QD, which will tell you respectively if the counter has reached PV or 0. The last function block that we will see is the so-called blink, also called clock or square wave generator. This block is used to generate a periodic signal on the output out. With the enable input, the signal generation is activated. With the time low and time high inputs, you specify for how long the output must remain false and for how long it must remain true. All these function blocks are very useful for developing PLC applications and provide reusable tools in various circumstances. In the following video, we will see how to use these function blocks for different applications and exercises, and we will see how they work in practice. In this video, we will see how to download and install codesys on a Windows computer. So, you have to go on the website www.codesys.com. That is the 3S software website, and you should go on to codesys store by clicking on this button. It will send you to this page where you can directly download codesys if you are registered and logged in. So you should click on login. I already have an account and you should create your one. But once you have created your account, you should simply log in and get back to the store page where you can download the version of codesys that you need, 32 or 64-bit. If you read and accept the conditions for the download, you can simply download the setup file. Once the download is finished, you can directly execute the file you just downloaded. That is a simple standard setup for a Windows operating system. So, once the extraction of files is complete, you can simply click next, read the license agreement and accept them, read this information and click next. You can select the destination folder for your installation, choose if you want a complete or custom installation of codesys. I would choose a complete one. So after this you can click next again, and after this, by clicking install, the setup will start installing codesys. When the setup is finished, you will have a simple icon on your desktop that you can use to start up codesys. In this video, we will learn the basics of codesys by opening it for the very first time. We will learn how to create a project and how the different features of codesys work in order to be able for us to create our first program and learn the first programming languages of the IEC 611313. Okay, so if you open codesys, you will see a window like this. You will need to create a project. You can do this by clicking on this symbol or going into File, New Project. And here you can select the folder for your project and the name of your project. Let's name this project Project 1. And then you can select if you want a project or a library. Libraries are a set of software, of functions, function blocks, and so on that can be imported in other libraries or projects. Libraries cannot be directly downloaded on a PLC. Instead, projects are complete projects that can be downloaded on a PLC. So for now we will look into projects, and as you can see you have different choices. You have an empty project that will be empty, therefore an HMI project that will contain one HMI device, and then you will have a standard project that will have one device, one application, and an empty POU implementation. Then you have another standard project with a composer. we will look into the standard project and we will create it by clicking on OK. Codesys will ask us now two things. Will ask us what device are we using for this project and what language should be used by the PLC PRG implementation. The PLC PRG is the POU that the standard project automatically creates. You can either delete that, rename it, and do whatever you want. So the device we choose right now doesn't really matter for us because we are going to use the simulation mode for codesys. But just as for you to know, you have between these standard devices the Windows V3 control in a 32 or 64-bit implementation, and this is meant for systems that use Microsoft Windows operating system. Then you have the RTE, that stands for real-time environment, that is a codesys extension for Windows that is meant to have a real-time environment on Windows for applications that need hard real-time constraints. Then you have all these four in a soft motion variant that is used if you need to use some motion control or motion simulation within codesys with the soft motion library. We won't see any of this in this course, so for now we can select codesys control Windows V3 64-bit, and we can create an implementation in ladder diagram. That is the first language that we will learn. By clicking on OK, after some time the codesys will create the project, as you can see in the left. This left part is the hierarchy or PLC configuration that holds everything you need for the project. In the PLC configuration there will be devices and software. All the things that you see under the PLC logic and the application regard software. Everything that is outside are devices. So right now we have this device that is codesys control Win V3. Its name is device, and by double clicking on it you will open a tab on this center part of the codesys environment with all the settings and parameters for the device. If you wanted to connect to an existing software, to an existing device, you would have to go on this communication settings and scan the network to get the device. Typically, a standard connection is by an IP address, so you would need to scan your network to find the device. And here you have many different settings for the controller. You will have the file, you can look for files in the file system of the controller. There are different settings about access rights, users, and many more. We won't explore this, all these parameters and settings in our course. So, by going down there, let's look at what we can add and how the first project is set up. As you can see, I wanna close the device tab, and in the software of the PLC you will see some things. First of all, you will see the library manager. The library manager is the repository that collects all the libraries that are imported on the project. The library manager works in this way. There is a library repository that is the set of all the libraries that have been installed in your codesys system. If you want to add one of these libraries into your project, you will need to go into Add Library and scan, look for your library with this menu, or searching it. You can search it using this text input. If you need to install a custom library into codesys, first you have to install it in the library repository. By clicking here, you will click install and browse in your file system for the library file. Then, once the library is installed in your repository, you can click on Add Library to add it in your project. All the function block that are present in libraries can be directly accessed by the POUs that you write. So, let's move on to the other components that we see under our application. Here there is the task configuration. The task configuration is about the scheduling of tasks within the PLC operating system. We talked about the tasks and processes, cycle times and priority, and here we will see all of that. Under task configuration you will see the list of tasks that are being scheduled within the operating system of the PLC. As you can see here, we have just one task that is called main task, and by double clicking on it we will see all the details of this task. We will see its priority here that can be set, values from 0 to 31. In the codesys notation, a low number means high priority. So this task that has a priority equal to 1, it means that the priority is really high. Then here you can see the cyclic time of the task. That means how often the task is called with all the software, all the programs that are attached to it. And here you can see that it is being called every 20 milliseconds. This can be also changed. And another thing you can see here, that you can enable a watchdog. A watchdog, as we said, is the system that will send the CPU into a stop state if the workload of the CPU is unstable, meaning that the deadlines are being missed too often. And here you can set a time. For example, if I write here 40 milliseconds, what will happen? It will happen, you will see that if the task takes more than 40 milliseconds to execute, it will send the CPU into a stop. Here you can write a sensitivity, meaning how many times the deadline can be missed. If I write here 5, for instance, after 5 times that the execution time of this task exceeds 40 milliseconds, it will send the CPU into stop. For now, let's disable the watchdog. Under the main task, you can see all the programs that are being called from the task. Here, as you can see, we have only the PLC_PRG program. That's it for the task configuration. Now we will look at the PLC PRG POU that has been created automatically. By double clicking on it, we will see two parts of the POU that we already discussed. This part is called the declaration, that is where we create and write our variables, and this is the implementation, that is where the actual code will be written. Now, if in this part we can create our variables, all the variables that belong to the POU. As we talk, we have seen that there are many different types of variables, both about visibility and type of variable. Here, as you can see, here there is written var. Var means local variables. So all the variables that I will write between var and var will be local variables to the POU. For example, if I write here variable 1, this variable will be a local variable. Let's see how to define variables. There is a specific syntax to define variable, that is, you should write the name of the variable, then you should write colon, so here, then the type of variable. For example, we could write a Boolean variable, writing bool. If the type is a standard type, you will see it becoming blue. And then semicolon. In this way, we have defined a Boolean variable with the name variable1. This is a local variable for the POU, meaning that the POU can write it and read it, but it is not accessible from the outside of the POU. We could also write some input variable by writing the here var underscore input. If you press enter, you will see that codesys will automatically write the end var syntax. Here I could write my input variable 1 colon, let's say an integer variable, int, semicolon. Now we have a POU with a local variable called variable1, Boolean variable, and an input variable 1 of type integer. Then, in order to create an output variable, it is very similar. We write var underscore output, enter, and we could create an output variable 1 colon, let's say a real variable, real, semicolon. There's another type that we saw, that is the var input output. You should write var underscore in underscore out, and here we could say write a, I don't know, IO variable 1. Let's say that this is a string, semicolon. So the input variable can be read by the POU, but it won't be written by itself, because the POU cannot write input variables. On the other hand, the output variable will be written by the POU, but cannot be written from the outside. The in-out variable instead can be written and read from both outside and inside the POU. So we created all these variables. Let's see other features of the codesys. So I will erase these variables for now. In order to save a project, you can click on this icon and you will save the project. The project itself will be saved as a file in the folder you specified with an extension that is .project, as you can see up here. If you make any modification on your program, you will see an asterisk here that it will tell you that there are some modifications that have not been saved still. If you click save, you will see it disappear. There's another thing. The project file does not carry with itself all the libraries and information of the project. This means that if you open a project file in another version of codesys, you could have some compatibility issues. In order to prevent this, you could also save a file in another format, that is the project archive, by going here, File, Project Archive, Save Archive. And here you can select what to import within the project archive file. the extension will be .project archive, and in this way you can write a more complete project file. It will be much more heavier, will have a bigger size, but it will surely be compatible among different versions of codesys. In the next videos, when I will provide you some examples or exercises, I will always provide you the project and the project archive file. You should always try to open the project, and if it gives you some errors for incompatibility with your codesys version and mine, you should try to open the project archive file. Okay, now we can see some other things. I can, by right-clicking on applications, we can add other objects to the application, to the software of the PLC. For instance, we could create other POUs by going here and clicking add object POU, and as you can see, we can specify a name for the POU, a type, meaning program, function block or function, and an implementation language. For example, if I wanted to create a function block in structured text, calling it fb_test, I would need to set this window in this way: function block, structured text, and click add. As you can see, a function block has been added in the PLC configuration. And then I could create here in my program a function block with the type fb_test. I could call it fb_test instance 1 colon fb_test semicolon. In this way I created an instance of this FB in my program. Now let's erase it and we see some other things of codesys. As we saw previously, we have seen that there is another type of visibility for variables, that are the global variables. Global variables are defined in a different container in codesys. You can do this by right-clicking on application, selecting add object, global variable list. You can call it GVL, okay, and as you can see, there is a new object in your PLC configuration, and here you have a list where you can create your own variables. As you can see, there is also this little string, attribute qualified only. This means that in order to access the variables in this container, you should specify the name of the container, meaning that if I wanted to access the variable in a POU, I write this, I would have to say gvl.name of the variable. If you don't write gvl dot, it won't work if the attribute qualified only is present. So I typically erase it, so I could just access the variable by writing name of the variable without specifying the name of a repository. In my opinion, it is lighter and easier to do, but you're as well free to leave it. So this is how you create global variables. Global variables are accessible from all the points in the PLC software, programs, FBs and FCs. Let's write here a global variable. Let's say global variable 1, type Boolean. Okay. Now moving on, let's see something else on codesys. On codesys there is an useful feature called visualization. If you click on add object visualization, you will see this window. It will ask you to import this System library, Symbol library. Let's do it. By clicking Add, you will see that in your hierarchy a new object called a visualization. Visualizations are simple screens or HMI surrogates that run within codesys. They are very useful to debug and to have to build simple HMI kind of things on codesys to interact with the actual project. As you can see, we have this visualization. We have many tools that we can use to create our visualization, both graphic tools here and also control tools. We could have buttons and switches and so on, many others. And this is very useful because we can actually interact with the program like we had a panel operator on our side, even though we haven't. In all the exercises and example that I will provide you, I will also create a visualization that will help you understand the process at hand, and it will also provide you a way to interact with the application. I will delete this, and here it also created a visualization manager. The visualization manager is a set of settings for the visualizations. Okay. Now let's see another thing for the project. Before, when you have written some code and that you want to download on your PLC, there are some steps. First, you need to build the code or compile the code. In order to build the code, you can either click on this symbol here or going to build. An alternative is to simply press F11. By clicking build, you will see down here the build going on. And then it will say if there are some errors or warnings within your PLC software. Now, obviously, we haven't written any code, and there are no errors. If you want to go online on your PLC, you should go on online and click on login, or simply click on this symbol right up here. This will work if you are connected to your system. We are going to use the simulation mode in this course, so in order to go online using simulation mode, you will need to click on online and click on simulation. By clicking on simulation, you will see down here this red simulation string written down there. This means that the simulation is active, and if you try to go online, you will download your software on a virtualized PLC present on your Windows system. Now, if I click online, I could directly download the application that we wrote. Now it's an empty application, we won't see anything, but I can actually download it on the virtual PLC and run it. By clicking on login, you will see that codesys will tell me that there is no application right now on the device, and codesys asks me if I wanted to create it and proceed with the download. I will click yes. It's generating the code. Down here you can see what codesys is doing, and this is the online view for codesys. Right now the program has been downloaded on the virtual PLC and the PLC is stopped, as you can see here. If I want to start the program, I will have to click this play button or click F5. By clicking start, now the PLC is in run mode. The PLC is executing the code that we wrote. Right now there is no code, so we won't see anything, but the actual virtual PLC is actually running the program, and it is online and working. When we will try to build our first programs in a programming language, we will see all the debug tools that are present in codesys while online, and how to interact with variables and code when we are online and running a program. For now, let's go offline here, and we will see something else. If we want to share some variables with some external device, we could add here, by clicking on application, add object, we can add a symbol configuration. Let's click OK. A symbol configuration is a list of the variables that are present in your project that need to be shared with some devices using some server functionalities. By going into symbol configuration and clicking build, it will ask to build before we can do this. We can share the variables with some other devices by selecting them from this menu. Right now we have no variables other than constants and configuration variables that are coming from libraries, but we can actually share these variables. This configuration is typically used to share variables with HMI, with panels, using some internal protocols such as OPC UA or Modbus TCP, or some other proprietary protocol of the PLC manufacturer. Now I will delete this, and later on we will start from this project. Let me delete some things before we continue. I will delete visualization manager, so we start also this GVL. So we will start from scratch and start learning the ladder diagram language from scratch. We will create some simple programs first, and then we will see how to interact with our application. In this lesson, we will start from the standard project in codesys and we'll learn the basics of the ladder diagram language. We will learn how to create the first program lines, and we will see what are the basic operations that you can carry out in ladder diagram. In the standard project, as we have already seen, there is a POU already implemented in ladder diagram called PLC_PRG. If we open this, we will see the first part, that is the declaration where we can define the variables, and the second part that is called implementation. That is where the actual ladder diagram lines of codes will be written. So, for the sake of this first lesson, let's declare some variables in the declaration part of the program. So in this video we will not care what are the actual meaning of the variables. We just want to introduce the basic concept and what the operations in ladder diagrams do. So we will define three variables right here, three Boolean variables called A, B and C. So I will write A colon bool semicolon, B colon bool semicolon. In order to move the text, to align the text as I'm doing, you can use the tab key. So C colon bool. Okay, right now we have three variables. We are still not doing anything in the code since the implementation is empty. Ladder diagram is programming languages with horizontal lines of codes, of graphical code, that are executed from top to bottom. Every line of code is meant to work as a simulated current flow. meaning that there is some current running from the left part of the line to the right, and the contact and coils that are placed within the line will dictate how the current flows and how the logic is computed. There are two main components for the ladder diagram operations that are called contacts and coils. Contacts are placed in the left part of the line and are used to evaluate conditions while in a ladder line of code. While instead coils are placed in the right part of the ladder line, and they're meant to set some variables to desired values. Contacts and coils can be added using the buttons that are displayed in this toolbar up here. For instance, if we insert here a contact, with this button, Insert Contact, you will see the symbol that is placed here. This is also called a normally open contact. Here you can see that there are some question marks, and upon this question mark you should write the variable that is connected to this contact. For instance, we can use the variable A. What does this contact mean? It means that the current flow coming from here, from the left part of the line of code, will get through A only if A is equal to true. If instead A is false, the current flow will stop right here. Right now this line of code is not doing anything. As you can see, by placing the mouse over A, it says that the code A has no effect, meaning that the current will reach this point and not actually do anything. In order to carry out some action, we can, on Boolean variables, we can use the coils. So contacts are used to evaluate the value of Boolean variables and to actively decide the flow of the current. Coils instead take the value of the current that is flowing towards them and set accordingly the value of Boolean variables. For example, if I click here and add a coil, that is done by using this button over here, we will have a coil placed on the right side of the screen. Also in this case there are some question marks that should be substituted with the actual variable that we want to use. For instance, we could use variable C. How does this coil work? If the current reaches the coil, the C variable will be set to true. Otherwise, the C variable will be set to false. This line of code here is actually setting the C variable equal to the A variable, given the fact that if A is true, current will flow to C, and if A is false, current will not flow to C. Let's try to go online and test this code. In order to go online, you can build and log in, but if you click only the login button, the build operation will be carried out anyway. So let's click login, and let's click yes to download the application on our virtual PLC. Take in mind that you have to enable the simulation mode. If you don't have the simulation mode, go on to online and click simulation. Let's click yes. And now we are online and the CPU is not running. As you can see here, there is the stop, it's in a stop state. Up here we can see the current value of the variables. By clicking start or F5, the CPU will start running the program. Right now the program is actually running, and this line of code is being executed at each PLC cycle. So, right here we can try to modify the values, the online values of the variables with this very useful debugging tool. In this column you can see the current value of the variables, and in this column you can set some values to use onto these variables. For instance, if I click here on the A row, you will see that this true value will appear. Right now the A variable is still false. In order to overwrite the value with the prepared value, you should press Ctrl and F7 together. Alternatively, you can go onto Debug right here and click on Write Values. If you click Ctrl and F7, you will see that A will become true, and also C is becoming true because this line is executing. If I click here again and I press Ctrl F7, you will see that also C will become false. This line of code means to set C equal to A. If I write the B variable, nothing else will happen, since the B variable is not used nor set in any part of the code. Instead, if I try to write the C variable, I will see that it won't become true, because it will be instantly overwritten by this line of code, setting it to false. You can also modify the value of Boolean variables or any variable by double-clicking on the contact or coil that represents that variable, and clicking Ctrl F7. When you are online, if you want to stop the PLC and reset the values of variables to the default one, you can click on Online and use the reset worm command. By clicking on the reset worm command, you will see that now the CPU is in a stop state and all the variables have become false. It is also possible to specify some initial value of the variables in the declaration part of the program. For instance, we could want the B variable to be true at the startup of the PLC. If I write right here, colon equal true, the B variable will be true when the PLC program starts. Let's try to go online. Right now we are going online with a program running on the already loaded on the CPU, but the program we have on our codesys environment is different. The application changed since the last download. Codesys is asking us what do we want to do. We can log in with an online change. That means that the code will be changed on the fly on the program. So at the next cycle it will execute the updated code. We can carry out a login with download, meaning that the PLC will be put in stop mode and all the variables will be reinitialized. Or we can log in without any change. This is not very useful because the program that we will be seeing will not be the one that is currently executing on the PLC. So, for now we can log in with download. Take a look at this checkbox. This checkbox is really important because if you tick this box, you will also overwrite the so-called boot project. The boot project is the project that will be run at the start, at the power on of the PLC. If you don't update the boot project, you will not overwrite the application written on the PLC at the startup. So it is often you will often need to check this box. So let's carry out a download of the program on the PLC, and right now you will see that the B variable is already true. That is because we initialized it in the declaration. Okay, Let's see some additional operation that you can do with Boolean variables. There is an important operation that is called the negation, since you could either use a negated contact, also called normally closed contact, instead of this one. So let's click on this contact and delete this by clicking the delete key on your keyboard. And let's place right here a negated contact with this button. And let's write variable A right here. This contact works in an opposite way with respect to the normal one. Current will flow if A is false, and current will stop if A is true. So, in the end, this line of code is actually setting C to the opposite of A. Let's download. Let's now carry out an online change. And as you can see, A is false and C has become true. If we set A to true with Ctrl F7, we will see C becoming false. That is great, and we can carry out the same kind of operation. We can also negate directly a coil by right-clicking on the coil and clicking on negation. This line of code is the same that we use, is carrying out the same thing that we did before, because we are negating A and negating C again. So right now we are setting again C equal to A. You see that A is true and C is true. And now A is false and C is false. Okay. Let's go offline, modify this code and see some more operations that we can carry out in a ladder diagram. Let's see specifically the series and the parallel. So let's delete this line of code. Let's right click right here and select the insert network option. And let's add two contacts by clicking the insert contact button, 1 and 2. And then let's click here and add a coil. Let's write here the variable A, here the variable B, and here the variable C. And let's try to evaluate what is this program doing. The A contact and the B contact are in series. This means that current will flow only if both of them are active. This operation is also called an AND operation, meaning that the current will reach the C coil if both A and B are active. We can see this by going online and carrying out a download. Now we will see the B is true, but the current is not flowing because it is stopping right here. Let's reverse their value by setting only A to true, Ctrl F7, and now we can see that the current is stopping right here on B. The only condition that will lead the activation of C is if both A and B are true. And right now you can see that C has become true because A and B are both true. Okay, let's go back offline. Let's remove for now this initialization of B and let's see the parallel operation. So let's delete this B contact by clicking it and pressing the delete key on your keyboard, and let's add a parallel contact. In order to add a parallel contact, you have to right click on the A coil and click on Insert Contact Parallel below. We have a contact here, and let's set it to the B variable. Okay, let's evaluate what this contact is doing. Current will reach this point if either A or B are active, one of them or both of them. This is also called an OR operation, meaning that C will be active if A or B are true. So let's go online with a download again. Press the start button and we see that now both of them are false and C is false. If we set A equal to true, C will become again equal to true. If we instead set B equal to true, C will again become equal to true. And if both of them are equal to true, C will become equal to true. So these are the series and parallel operations. Now let's see some more operations that can be carried out using coils. As you can see right here, there are two other kinds of coils, the set coil and the reset coil. So for now, let's delete this B contact right there, and let's also delete this coil, the C coil, and we'll now see what this coil actually do. These coils are called the set and reset coil. By adding a set coil here for the C variable, this coil works in the following way. If current reaches the coil, the set coil, the variable will be set to true. If the current does not reach the set coil, the coil won't do anything. It will not overwrite the value. Let's see what this means in practice. Let's go online and download the program, and let's start. Okay, right now the current is not reaching the C coil, the C set coil, and nothing is happening. If A is equal to true, Ctrl F7, C is becoming true. This means that the current reaches the C set coil, and the coil sets the C variable. Right now, if I reset the value of A to false, as you can see, C is still true, because this is how the set coil works. Right now the current is not reaching the set coil, so it won't carry out any operation on the C variable. This coil only sets the value when the current reaches it. Okay, let's now see the reset the reset coil. The reset coil carries out the opposite operation, meaning that if the reset coil is reached by the current, you will have the C variable set to false. So let's add down here another network by right-clicking on the network and clicking Insert Network below. Let's insert a contact right here for the B variable, and let's add right here a reset coil for the C variable. Let's see what this program should do. If the A variable is true, C will be set to true. If the B variable is true, C will be set to false. Let's see right here what is happening with the download. Let's start the program, and if I set the A variable to true, C is becoming true. If I set A to false, C will remain true. By setting the B variable to true, C will become false. And this is how the set and reset coils works. In the following video we will try to create a simple program for a simple simulated machine with some assumptions, and we will learn how to use these functionalities in order to build some machine logic. In the previous video we have seen the ladder diagram language, and we introduced some of the basic operations and tools that are being used in ladder diagrams networks, such as contacts and coils. Right now we will try to write a more consistent program for a simplified machine in order to simulate an automation environment. So, starting from the program we developed, let's delete both networks and all the variables that we place inside our program. And right now, let's try to add some variables to simulate a real machine. All these variables will be local variables, and we will fake there being inputs or outputs of our process. So, in this declaration of the POU, let's write some comment in order to see which ones are inputs and which ones are outputs. You can write a comment wherever you want by writing a double slash. So let's write double slash inputs, and let's say that this machine has a start button that will be a boolean variable, and let's say that we also have a stop button that is also a boolean variable. This is a generic machine, so let's assume that we have an emergency button. Typically, emergency buttons are so-called normally closed, meaning that they are connected to an input, a digital input that will be true when everything is okay and will be false when something is wrong. So let's write here a variable called emergency okay, boolean variable. Then let's assume to have some safety barriers in our machine, and let's have a variable called safety barriers closed. Again, a boolean variable. Okay. And then let's assume that we have a single output for this kind of process that should be used to start the machine. Let's not get into the details of what this machine does, and let's assume that we simply have an output that will have the machine running. So let's have this output called machine running. That is a boolean variable. Okay. So let's also add some other stuff. Let's assume that we also have an output that sets the machine velocity. So let's call this machine velocity. We don't care right now if this is representing the productivity of the machine, meaning how much pieces it is producing for a minute, or maybe the RPM of a master motor. Right now we just don't care. And let's say that this variable is an integer type variable. Okay. Right now we should also add some inputs for the management of this machine velocity. So let's say that in our machine we have two buttons on our user interface, human machine interface. A button to set a low velocity and a button to set a high velocity. So in order to do this, let's add two boolean variables, a low velocity button, boolean variable again, and a high velocity button. Okay, we should also know what are these velocities. So let's also have some integer variables. For instance, a low velocity variable, integer variable, and let's place an initial value to this variable, for instance 200. So let's write : equal 200 semicolon. Okay, let's also have a high velocity, an integer variable again. Let's say that the high velocity is equal to 1000. As before, we just don't care about what these numbers are representing right now. Okay, so let's start to write some code. And let's right click here and insert a network. Okay, so let's start with the management of this machine running output. So our program will start with machine running off, and we should decide which are the conditions that should lead to a startup of the machine. Okay, so since we are deciding when to enable, when to start the machine, we should just add right here a set coil at the end of this network. So I will add a set coil right here called machine running for the variable. Okay, and right here we should write the overall condition that will lead the machine running variable to become true. So in order to start the machine, we should surely have the emergency OK and the safety barriers closed. So let's add right here a contact for the emergency OK. And since we need both of these conditions, we will create a series of contacts with another contact right here that is safety barriers closed. Okay. Then, in order to start the machine, we should also need the start button, obviously. Okay. So right now, if we have the emergency OK, the safety barriers are closed, and we press the start button, the machine should start running. Let's add another condition that we will insert by putting right here a negated contact. Sorry, let's click here and place it onto the right. A negated contact with the variable stop button. This is done to avoid the startup of the machine if someone is pressing simultaneously both the start and stop button. In this way, if the stop button is being pressed, the flow will stop here and the machine running will not be set. So in order to start the machine, you have to press the start button while not pressing the stop one. Okay, this seems to like a nice condition to start the machine. Let's now evaluate a condition to stop it. Let's insert a network right here, and since we are deciding when the machine should be stopped, we should evaluate when to set the machine running variable to false. This means this is equal to use a reset coil. So let's put a reset coil connected to the machine running variable. Okay, so let's think about what are the conditions that should stop our machine. Well, first of all, if someone presses the stop button, obviously the machine should stop. So let's place right here a normal contact for the stop button. Okay, then we should also stop the machine if someone presses the emergency button, meaning that the emergency OK condition is no longer true. So let's right click right here and let's insert a negated contact in parallel. Why is this in parallel? Because either one of these conditions should stop the machine. This is a NOR type of operation. So let's write right here emergency OK. And then we should also stop the machine if someone opens the safety barriers. So let's right click here again, insert a negated parallel contact for the safety barriers closed. Okay, this is great. We wrote two nice conditions for our machine to start and stop. And let's now go online and try this. I will download my application. Be sure to have the PLC, the codesys environment in simulation mode. Okay, and let's start the operation. Okay, we have our machine running that is false right now. Let's place the safety barriers closed and the emergency OK conditions. Machine running is still off, still false. So let's press the start button. Okay, and let's release it. Okay, machine running has become true. Even if we release the start button, that is exactly what we wanted. Let's click on the stop button. Okay, machine running has become false. For instance, let's try to press the start button while we are also pressing the stop button. Click here and press Ctrl and F7. And as you can see, the machine running is not turning into true because the flow is stopping here. Okay, so this works fine. Let's log out, and now let's try to add some additional lines of code to handle this velocity settings and velocity button. Okay, so let's add a network below, and let's try to evaluate these two buttons, and we should also set this variable according to the button being pressed. In order to to assign a value to a variable, there is one block that is being used that is called the move block. In order to place the move block into a block, a function block or a function in a ladder diagram network, you should use one of these two commands in this toolbox. That is the box or the box with enable output. Sometimes it is useful to have this box with enable output, because this is a setting that will add two inputs, an input and an output, to your block. And you will see it right here. You can simply click on this and drag it. And as you can see, this is what happens. It will create a block with some question marks, and you will have an enable input that if it is true, the block, the function or function block will be executed. Otherwise, it won't. So let's write on these question marks move. Okay, so now codesys has recognized the move function block, and let's see how this works. Move is a function block that will move the value that is placed in this input onto this output. So we should place the low velocity, for instance, the low velocity value onto the machine velocity variable. This is the same as setting machine velocity equal to low velocity when this contact is true. So this should happen when the low velocity button is being pressed. Okay, let's add another condition very similar to this one. So in order to avoid some issues, let's say that we want to overwrite the current velocity only when the low velocity button is being pressed, and the high velocity button is not. So that in this way, if someone presses both buttons at the same time, you will not have some issues. So let's click right here and insert a negated contact connected to the high velocity button. Okay, this is great. We should do this again for the high velocity button. So we can just copy and paste this network. Let's click on the network until it is highlighted. Press Ctrl and C and Ctrl and V. And as you can see, the network has been copied and pasted. Let's edit these values. So right here we should have the high velocity button. Right here we should have the low velocity button. And right here we should have the high velocity. Okay, let's try this feature by going online. Let's apply an online change for now. So, right now the machine velocity is 0. Let's press the low velocity button. Okay, machine velocity has become 200. Let's press both buttons simultaneously. And as you can see, nothing is happening because the flow for both networks is stopping right here. And let's now press only the high velocity button. Okay, that's great. Machine velocity has become 1000, so this is working quite fine. Okay, let's for now carry out a reset worm in order to reset the variables. And right now, maybe there is some issue that we should take care of. So, in order, as we try to start the machine by setting the safety barriers OK, emergency OK, and start button, we can see that now machine is running, but the machine velocity is 0. Right now we can start our machine with a 0 machine velocity, and this for our application maybe could be an issue. So let's try to fix it. We have two strategies. We could ensure that machine velocity is different from 0 when we are starting our machine, or maybe we could ensure that machine velocity will always have a valid value inside of it. So let's try both ways. We should, in order to evaluate if machine velocity is a valid value, we should add another condition in this series in order to start the machine. So right now we should evaluate when machine velocity is different from 0, is not equal to 0. And in order to do this, you can see that right here under the math operators in the toolbar, we have many different blocks that can be used for this purpose. In particular, we have these blocks that are used for comparison of values. For our purposes, we can use this NE block that is a not equal comparison. By dragging it and placing it here, you will have this block that will enable this output if the two inputs are not equal. So right now we should evaluate if machine velocity is different from 0. Okay, let's try this again. Let's go online, and for this time let's download in order to reinitialize the variables. Let's start. Let's close the safety barriers and the emergency OK, and let's set the start button. Okay, as we can see right now, machine running has not become true. This is due to the fact that, as we can see, the flow of current is stopping here, since machine velocity for now is actually equal to 0. So let's solve this issue by simply pressing one of the two velocity buttons. Right now machine velocity is equal to 1000 and the machine started running. Okay, this is fine. Let's see something else on the ladder diagram. The alternative way to do what we just did, meaning that we should always be ensured that machine velocity has a valid value within it, we could simply initialize the value of machine velocity equal to low velocity. It is possible for us to initialize variables to the values of other variables. Okay, this is fine. However, maybe at the startup of the PLC, low velocity will not be maybe low velocity is some variable that comes from the HMI from another device. So maybe when the PLC starts, we may not be sure that at the first cycle of the PLC, low velocity will actually be different from 0. So, in order to try to do this, let's try to add some other lines to carry out this implementation. So let's insert a few networks on the top of our programs. Okay. So let's say that we should wait for the low velocity variable to have a valid value in order to be sure to be able to run the machine. So let's create a variable, an internal variable. So I will write a comment here and say internal, meaning that it is not coming from an outside device. And let's say this, that is, the machine is ready. A Boolean variable. So, what should happen? If the machine is ready, actually all of these lines should execute. If the machine isn't, these lines should not be executed. So let's evaluate this. This is possible using the so-called labels and jumps. So I could simply write here, add right here a contact. Let's say that if the machine is ready, if machine ready, we could simply jump to a so-called label. You could add any label to any ladder diagram network that you wish. So let's right click here and click on the insert label. And let's call this label start of machine cycle. Okay, so let's say that if the machine is ready, we should jump to the start of machine cycle. If it isn't, it means that we are executing these lines, otherwise we are simply jumping right to this network 4. If the machine isn't ready, we should evaluate the low velocity. So let's say that if the low velocity is equal to 0, machine ready should still remain false. Otherwise, if low velocity is different from 0, machine ready should become true. So let's also place right here a not equal block that will evaluate low velocity. We said low velocity. sorry, I wrote this wrong, low velocity and 0. If low velocity is not equal to 0, we should move low velocity into the machine velocity. So let's carry out this by adding here a box with enable output, and this block should be a move. So let's place low velocity here and machine velocity here. Okay, and we can use this enable output. You can see this enable output simply takes the value of enable and place it on the output. So it's simply representing the value that is placed on the input. Okay, so if we get the low velocity different from 0, this will become true and this will become true. So we have placed this in this way. Then we should simply set the value of machine ready. Machine ready should become equal to true. Okay, so in the end, if machine ready is still not equal to true, meaning that this condition has not been satisfied, we should not execute all these lines. So we should jump to the end of the cycle. Let's right click over here, right click here, and insert another label on this empty network, and let's call this end of machine cycle. And right here, let's write a negated contact for the machine ready, and add right here a jump using the arrow to the end of machine cycle. So what is actually happening right here? Sorry, right here I wrote this is end of machine cycle off. Okay, so what is actually happening? When the PLC starts, it will evaluate if the machine is ready, meaning that we have already a valid value on machine velocity. Since we have not done anything on this variable, this will be false and this jump will not be performed. We will move on to this line. If the low velocity is different from 0, it will be placed onto the machine velocity and the machine ready will be set. So if machine ready is set, meaning that everything was okay, this line won't actually do anything and we will carry on with our cycle until the end. At the next PLC cycle, we will evaluate this line, machine ready will be true, and we will jump to start of machine cycle, and from every cycle after that, the 2 and 3 lines of codes will not be executed. If instead this condition is not satisfied, meaning that low velocity is in fact equal to 0 at the startup of the machine, we won't have machine ready, and we will directly jump to the end of machine cycle. So let's try this. Let's log in with download. Let's press play. Okay. Right now, machine velocity has become 200 because this line has been executed, and as you can see, machine ready is true. Okay, let's go offline for a moment, and let's say that right now low velocity is equal to 0. So let's put us in a condition in which the variables are not correctly initialized. Let's log in with a download and let's click start. Okay, right now you can see that machine ready is still staying false, and therefore this line, only these 2 lines are being evaluated. These 3 lines. At the 3rd line we jump to the end of machine cycle. So we can press whatever we want right here. Maybe we can press the high velocity button. As you can see, nothing is happening because this line is not being executed because we are jumping. We can also try and start the machine with these 3 conditions. The machine is not starting because this line of code is not executing. The machine will become ready once we place a valid value on low velocity. So let's write right here 200 on low velocity. Let's press Ctrl and F7 and we will have the machine ready becoming true and the machine velocity becoming equal to the low velocity. Let's click Ctrl F7. Okay, machine now is ready. And if now we start the machine by enabling the start button, the emergency OK and the safety barriers closed, Ctrl and F7, now the machine is running. Okay, in this video we have seen some stuff. We have seen how to create a simple program. We have seen the move operation for the ladder diagram code, the conditional operators. We have also seen labels and jumps, and how they can be used in ladder diagram. In the last video we have created a simple program for a generic machine using some ladder diagram functionalities. In this video we will try to extend this program by increasing the complexity and by using some of the standard FBs that have been discussed a few videos ago. So let's introduce some additional specifics for our program. So in this program we carried out the start of the machine in these 2 lines. We carried out the setting of the machine velocity in these 2 lines, and then we used these 3 lines and this last one to carry out the initialization of the machine if needed. Okay, so right now let's try to add some timer and some other function block to add additional functionalities. So let's write back here 200 just to have the machine already initialized, and let's say that we want to start the machine if the start button is and all the conditions are good to go, but mainly if the start button is being pressed for at least 2 seconds. So in order to do this, let's create a function block. Let's instance a function block. So as you can see right here, we used some blocks in ladder diagram. All of these are functions because as you can see we didn't have to instantiate any of this. We didn't create any copy. This move is not a copy of the same move of the move function block. Move is a function that is being used in different parts of the code. The same goes for this not equal and many others. So in order to create a function block we have to instantiate it, declare it in the declaration part of the program. So let's create a timer on by writing here, let's say timer machine startup. The type of this variable is a TON. Okay, so in order to do this we to carry out this functionality, we should set the machine running variable only if all these conditions have stayed true for more than 2 seconds. So, in order to do this, we can add right here a box in this position. Let's add a box without the enable output, and now we will see why. By dragging this here and by writing here on these question marks the name of the instance of the function block, in our case is timer machine startup. Pressing enter, you will see that this has become our TON. We want this signal going right into the input of the function block. And this is the reason why we didn't add the box with the enable output. Because in this way, if you recall how the ton works, in this way this variable right here will activate the ton. How does this function block work? The ton works in this way. When in becomes true, Q will become true after a delay specified by PT. In all this time, in must remain true, otherwise the timer is reset. So, in order for this thing to work, we could simply write right here the time we need. For instance, the T hashtag 2 seconds. Sorry. T hashtag 2 seconds. In this way, we have placed right here a time. This is great, it works, but maybe we could place this time into a variable, because it would be nice for us to be able to edit it without going to the specific point in the code. So, let's create right here another variable, a time variable, and let's say that this is the machine startup time, and the type of the variable is a time. And let's initialize this to 2 seconds. So T hashtag 2s semicolon. And let's write this variable right here. Machine startup time. Okay, this is great. Let's try this. Let's build our program. Let's go online with the download. Okay, our machine is initialized, so is ready. So how the program is executing, and the machine velocity is not 0. So right now we should just need to press to activate the emergency and the safety barriers, and then the start button. You should look closely at this value that will start increasing once the TON is enabled, and look at the machine running variable. You can look at it here or here. So I will enable right now the start button. The timer has started, and after a while, machine running has been set. So let's try this again. I will remove the stop button, set the stop button in order to stop the machine, reset the stop button right here, and this time I will try to press the start button and remove it before 2 seconds. Here I go. As you can see, the machine has not started because the tone has been reset before being able to enable its Q output. So this is working exactly how we wanted it to. Okay, let's go now offline. Let's log out and try to implement another functionality. Okay, so let's also say that we want to count the pieces being produced by this machine. And let's say that we know how much time it takes for our machine to produce a piece. Okay, so in order to do this, let's create another time variable. Let's say piece production time, I don't know, a time variable, and let's say that this is equal to 1 second. Okay. Then it could be useful to generate a periodic signal that has a period of 1 second. If you remember, we introduced a block in one of the previous lessons to carry out a similar operation. This function block is called blink, and this is a function block that will generate a square wave signal, meaning a Boolean variable that will be false and true for specified times. So, in order to do this, let's add a blink function block. All the function block that we have used, this ton, was in the standard library. Unfortunately, if I try to add a blink right now, let's call it blink piece production of type blink, and I try to build, you see that I get an error because the library where blink is placed is not available. So, in order to add a library, remember everything was in the standard library right here. As I click on standard and go on timer, here I see, for instance, the TOF, TON, and TP. The blink instead is in another library. If I don't know what is the library name, I can simply click on add library and write blink. Codesys will scan the libraries looking for the thing that I'm looking for, and here I have the blink in the library util. I add it now. I try to build, and right now codesys found the blink, and now we are good to go. Okay, so let's add right here another network below to implement this function. So let's insert a box right here, and let's say that this is our blink piece production. Okay, this is how the blink is placed right here. We need to specify a time for the periodic signal to be low, a time for the periodic signal to be high, meaning false and true, and then an enable input to start the generation of this signal. Well, the machine is producing only when it is running, so it would be fairly reasonable to assume that the enable of this function block should be the machine running variable. Okay, so in order to generate a periodic signal that has this period, we could have this one, the half of this time as time low and half of this time as time high. So the overall sum of these two will be this 1 second right here. So we could write piece production time divided by 2 and piece production time divided by 2 over here. Okay, let's go online and see if this works. Let's log in with the download. Let's start our PLC. Let's go over here and start the machine with these three conditions. 1, 2, and 3. And click Ctrl F7. After 2 seconds, the machine has started. Let's look at the blink. Here you go. You are seeing this out signal doing exactly what we want it to. It is blinking and its overall period is 1 second. Okay, now we can use this to count the pieces that are being produced. Let's go offline, let's log out, and think how can we do this? We could use a counter that is exactly the type of function block that should be used for this. So, if you remember something from our previous video, there are mainly three types of counters: the counter up, the counter down, and the counter up down. So, we should, since we are just counting in an upward direction, we could use simply counter up. So let's write right here a new function block. Let's instantiate it, counter pieces, let's say. And its type is a CTU. Okay. Then let's also create a variable where we should store the number of the produced pieces. Let's say pieces number, and this should be a word because the counter value of any counter is a word type variable. So in order to do this, let's add a box right after the blink function block, and this function block should be our counter pieces. Okay, this is fine because the out of the blink is going exactly into the CU input, and this is the variable that is being used to count, meaning that at every rising edge of this variable the value of the counter will increase of 1 unit. And this variable is actually having a rising edge every second. So this is great. We can add this variable in order to set this Q output, but right now we don't need to, so we can just write 0 right here. The CV output should go exactly on the pieces number variable that we created, and maybe we could reset the counter whenever the machine is no longer running. So for instance, we could insert a negated contact and remove this one with the variable machine running. Okay, now let's log in and try this. Log in with download, and let's start the CPU. Our machine has been initialized. Let's start it, double clicking every contact right here. Press Ctrl and F7, and after 2 seconds we are seeing this variable increase once every second. This is great. Let's try to stop the machine and let's see if this variable goes back to 0 by going over here, and let's disable the start button and enable the stop button. The machine has stopped and the pieces number has become 0. Okay, this is great. And let's try right now to modify the piece's production time. Let's say that we want one piece every 200 milliseconds, so much faster. Ctrl and F7. Let's start the machine again. So let's remove the stop button right here and enable the start button. Ctrl and F7. And as we can see, the pieces number is growing much faster now. Exactly 5 every second, meaning 1 every 200 milliseconds. So, in this video we learned how to use function blocks within our ladder diagram program. We learned that they need to be instantiated within the variable declaration and should be used with how to use them within a ladder diagram line of code. In the next videos we will learn about another language that is structured text, and we will see what are the pros and cons of using either ladder diagram or structured text. Remember that ladder diagram and structured text are the two most used IEC 611313 standard languages in automation. In this video we will see for the first time the structured text language. We will learn the syntax and how to carry on basic operations, and we will try to replicate the program we created for ladder diagram in this new language. So let's start by opening up codesys, and let's create a new project by clicking right here, and let's call it, for instance, project 2. Standard project. Click OK, and then we can select POU PLC underscore PRG in the structured text language and press OK. So here it is, this implementation of a POU of a program in structured text. You can see that the icon right here is changed from before. This icon is different for every language. And as I told you, the structured text language is a textual one, so you won't have networks like in ladder diagram, but you will have lines of codes in a more traditional way. Structured text is very similar to Pascal, but if you also have a computer science background, it will be quite easy for you to use for these basic projects. If you use Python, C, C++, C#, or many other high-level language, the structured text language is quite similar to them. So let's start by declaring some variables and see what are the basic operations that are used in structured text. So let's start by defining right here 3 variables, 3 Boolean variables, let's say A, B, and C, as we have seen before. And let's try to write some code in order to have some action on these variables. So, like any language, any textual language, in order to evaluate some conditions, to evaluate some property, you should use a conditional statement, meaning an if statement. For instance, you could just right here write if A is equal to true, then do something. The syntax for a conditional statement in structured text is this one: if condition then something, and in the end of everything you will have an end underscore if. If you write an if statement, the end if will be written by the codesys system on its own. For instance, we could write if A is equal to true, then B is equal to true. There is some difference between this equal condition and an assignment. To assign a value to a variable in structured text, you should use the colon equal operation. That is the same that we have used in the initialization of the variables. For instance, we could say if A is equal to true, then B is equal to true. Else, the else statement works right like this. You write else and then a condition. The end if must be in the end of the overall if statement with all the alternative choices. So we could write right here, for instance, B equal to false, colon equal to false. In this way, if we build our code, we will have no error, and we are simply putting the value of A into B. Actually, here in the conditions of a conditional statement, you could have simply a Boolean value. So if you are evaluating A equal to true, you could simply delete this, the equal to true part, and this would work in the same way. If A is the same as saying if A is equal to true. On the other hand, if you are evaluating a negated condition, you could say if not A. It is the same as saying if A is equal to false. So this would simply place the value of A into B, and we could just delete all of this and write B colon equal to A. This is the same line as a contact and a coil in a single line. Okay, then in order to have some more advanced lines of codes evaluating, for example, the equivalent of series and parallels that we've seen in ladder diagram, you can use an AND syntax or an OR syntax, meaning that if you, for example, want C to be the series of A and B, you could write that C is equal to A and B. Or if you are using a parallel, you could say that C is equal to A or B. The first line is the same of a series, and the second line is the same of a parallel. Okay, let's move on and try to write a program similar to the one that we have already seen in ladder diagram. So let's write right here the variables of the first program we did. So we had a few inputs. We had a start button that was a Boolean variable, a stop button. You can simply copy and paste them from your project if you don't want to write them. Stop button, we had emergency OK as a Boolean variable. We had the safety barriers closed as a Boolean variable. We had the buttons to handle the velocity, like the low velocity button, Boolean variable, a high velocity button, the Boolean variable. We had the values of the velocities, the low velocity that was an integer type, and high velocity. that was again an integer type. As the output, we had, for our outputs, we had the machine running volume variable and the machine velocity as an integer variable. Okay. So, in order to carry out our operations, let's follow the same way of thinking that we had on in the last project. So, when should we start the machine? We will have, of course, an if statement with a here we could write between these brackets our condition to enable to start the machine. If something, then we should have our machine running equal to true, colon equal to true. Here we could add another condition by writing an else if operation statement. The else if in structured text is written in this way: else if another condition, then machine running should be equal to false. Okay. These conditions should of course be mutually exclusive, meaning that they must not be together true. And we can simply write what we did last time. So if the emergency is okay and the safety barriers are closed and the start button is pressed and the stop button isn't, meaning and stop button, then not stop button, machine running should be set to true. Okay. Then in the condition to stop the machine we should have the stop button or the emergency not okay, so not emergency okay, or not the safety barriers closed. So what are we doing here? Our machine should start running if the emergency is okay and the safety barriers are closed and the start button is being pressed while not having the stop button being pressed at the same time. Here the machine should stop if the stop button is pressed or the emergency okay is no longer okay or the safety barriers are now open. I suggest you to write some comments in order to make the code easy to read. So I could write here a comment as we wrote the comment in the declaration of variables. So here I could say this is the machine activation condition, and right down here I could write this is the machine deactivation condition. Okay, this is good. And now let's see how to handle the velocity of our machine, meaning the buttons that we set right here. I forgot to initialize these variables. We set this one to the value of 200 and this one to the value of 1000. Okay, so right now we should, oh sorry, I deleted this by my mistake. Okay, so right now we should handle the velocity. So let's say velocity button management right here with a comment. And what do we want? If the let's say start from the low velocity button is being pressed and the other one isn't, so and the not high velocity button, then the machine velocity should be set equal to the low velocity. Okay. Else if the opposite condition, meaning that a high velocity button is being pressed and the low velocity button isn't, so and not low velocity button. In this case, then the machine velocity should be set equal to the high velocity. Okay. So, as you see, right now in only a few lines of codes, we have replicated the program that we did on ladder diagram. Maybe reading a series of conditions right here maybe it isn't really easy for you, but after some practice it will get easier. And as you can see, the structured text is really compact, and by having more complex code needed, you will have a much easier life with the structured text. So let's try to go online and test this code. So I will go into simulation and I will go online, and let's try to see if this first version works. I will start the machine. Let's first try the velocity button. We can edit the values of the variables using this table or by double clicking beside the variables in the code. So if I set the low velocity button, I will see that the machine velocity has become 200. If I set this to false and enable the high velocity button, I will see the machine velocity going to 1000. If I enable both of them, I won't see any change, because now neither this condition nor this is enabled. So this works fine. Let's see the activation and deactivation of the machine. So let's set the emergency OK and the safety barriers closed. And let's set the start button. Ctrl and F7. As you can see, the machine running is true now. Let's reset the start button and, for instance, press the stop button. Stop button has been pressed, machine running is now false. So everything is going fine for what we intended. So now let's carry out some modifications that we discussed on the ladder diagram. First of all, we may also add here as a condition the necessity of having the machine velocity not equal to 0 in order to start the machine. This is very easy because we could simply add here an AND condition that is the same as using a series in the ladder diagram, and write right here and machine velocity different from 0. The symbol of different is this one. You should write a lower than and a greater than 0. This means not equal in structured text. This is the only symbol that is not quite intuitive. All the other ones are quite simple. You should write equal to verify if something is equal to another variable. Greater than, greater or equal is written in this way. Lower, lower or equal. So let's move on, and this condition will also evaluate the machine velocity. Now let's carry out the modification that we did on ladder diagram. So we want to evaluate all this code only if for instance, what we said in the ladder diagram program, we want to set the low velocity equal to the machine velocity in an initialization part of the program, and maybe we could want to to stop the execution of code, so to not execute all this code if the low velocity is, for instance, equal to 0. That means that maybe something is wrong, maybe the values that are coming from outside, from an HMI for instance, are not being processed in a correct way, so we don't want the machine to start. So let's write here a comment by saying this is initialization procedure. So let's create an internal variable right here, internal, that says that is called machine ready, a boolean variable. And let's write right here that if the machine is not ready, if machine is not ready, we should evaluate if the machine is ready. So we could simply write that if the machine is ready, we should look into the low velocity. So if the low velocity variable is not equal to 0, it's different from 0, then right now we don't have an indif written automatically, we can simply add it manually. Then we would want our velocity, machine velocity, to be equal to the low velocity. And then set the machine ready variable to true. Okay, so right now, in order to prevent any line following this to run if this condition is not satisfied, we could simply add right here an else condition, meaning that if the execution ends up in these lines, the machine is not ready and it won't be ready, so this code must not be executed. We could simply add right here a return statement. The return statement is useful in structured text to return from the execution of the current POU. If a return execution, a return instruction is being executed, the flow of the code will stop right here in the current PLC cycle, and we resume from the top at the next one. So if the machine is not ready and the low velocity is equal to 0, the program will return, and these lines of code will not be executed. So let's try this by going online with the download. If I press start, since right now the machine velocity, the low velocity is not equal to 0, I would expect the machine ready to become immediately true and the machine velocity to become 200. Let's see. Oh wait, I don't want to set this manually. I will simply press start, and as you can see, this has occurred, and right now these lines of codes are running. So if I press all the condition to start the machine now is running. Okay, this is fine. So let's now let's say online just for a moment and carry out a warm start of the PLC. And before starting the machine, let's set the low velocity of the low velocity to 0 before starting the PLC. So right now the low velocity is 0, and if I start the program, I expect the machine ready to remain false, and these lines of codes should not be executed at all. So I press start. As you can see, machine ready is not true, and if I try to start the machine with these conditions, Ctrl and F7, the machine is not running, and by pressing also the other buttons, they are not working. If I set the value of the machine low velocity to 200 while having all this condition and the start button pressed, right now the machine starts. Machine running is equal to true, and the machine velocity is now equal to the low velocity. So, as you can see, the structured text is very compact. Maybe you have to wrap your head around some syntax, or maybe the aspect that all this code is executed cyclically at every PLC cycle. But on the long run, structured text is, in my opinion, the best programming language for PLC. It is the most flexible, most compact, and it will be very easy to structure some code, to write quality code using structured text. In the following video we will see how to use the classical standard blocks in this program in structured text. In this video we will see something else in the structured text language. We will try to do some modification to this simple project in order to implement some standard function block features of codesys in a similar way that we already did for the ladder diagram language. Okay, so let's recall what we did in this project and what we should do now. Well, we handled the machine start with these lines of code. We handled the velocity change using buttons in this part of the code, and right here we handled a correct initialization of the machine. Okay, so right now we would like to have some additional features. The first one would be a delay, meaning that the user, in order to start the machine, should hold the start button for at least 2 seconds. And to do this, as we already did the ladder diagram, we should need a TON function block. So, let's go right here in the internal variable definitions and let's add a TON. Let's call this timer machine startup as we did before, and the type should be TON. And let's also define the time variable for this TON. A machine startup time of type time equal to t#2 seconds. Okay, so right now we have a TON declared in the variables. Now we should somewhere call this function block. Let's see how function blocks are meant to be called in a structured text language. In order to call a function block, remember you can do this in whichever line you desire. You should write the name of the function block, so in this case is timer machine startup. Open a bracket and close it. Place a semicolon, and in here you should specify the inputs and outputs in the following way. If you press Ctrl space, you will see that codesys will suggest you what are the inputs and what are the outputs. The inputs are the one with the arrow facing this simple rectangle, and the outputs are the one with the arrow going outwards from the rectangle. So if I double click on in, it will write in, and in order to specify which is the input, you should write colon equal. Then here you could write something. Then you place a comma and specify the second input, that is pt, colon equal, comma, and here you should specify the output. In order to specify to specify the output, you should write the name of the output, for instance ET, and the syntax to specify where the output value, in which variable the output values should be put. You should write equal, greater than, in order to make this kind of an arrow symbol in a textual way. Here you write a comma, Q again, equal, greater than. Okay, and in this spots you can specify which variables you want to use. Remember that you can also leave them empty. There is no need to fill them all. The only ones that need to be filled are the input-output variables that we didn't use here, and the time and the TON does not have any input-output variable. It has only inputs or outputs. As you can see, this is quite tricky to write all of this, and in codesys there is a simple feature in order to a really useful feature that can be used to simplify this process. If you press the F2 button on your keyboard, you will see that this input assistant window will be open. And if you go into text search, you can simply write the name of the function or function block that you want to call. If I start writing timer machine startup, you can see that I find my function block of type TON. If I click OK, as you can see, codesys has already written the call to my function block. So my suggestion is that whenever you need to write a call to a function block, you should use this simple tool. It's very faster and easy. So let's change the implementation of our machine activation condition. So let's move this call, Ctrl X, right here after the comment, Ctrl V. Okay, so recalling what we had in our ladder diagram code, we should have that input condition for the tone to start up is actually the condition that we are checking right here. So we could simply copy all of this and paste it right here in the in. In order to make this a little bit more readable, you can start a new paragraph. So let's press enter here after every variable in order to make this more easier to read. Okay, so the in should be equal to this end sequence. The PT should be equal to our machine startup time. Okay, and we can simply leave the Q and ET free without putting them into any variable. Then we should modify this if statement in order to start our machine. And then to do this, we could simply write the timer machine startup.q. In this way, we add that this condition will start the timer. After a machine startup time delay, the Q output will become true. And right here we check if the Q output has become true, and we set the machine running variable. Okay, so right now we implemented the TON functionality. Let's go online and test this. Start with a download. Let's press start. Okay, and let's now look into this machine running variable. I will place all the conditions and I will now expect this variable to become true exactly after 2 seconds after I press Ctrl and F7. Let's try this. Ctrl F7. 1, 2. Here. Machine running has become true. Let's stop the machine right now by clicking the stop button. Okay, it has stopped. Let's try this again. 1, 2. Okay. So this part of the program works exactly how it worked in the ladder diagram. Okay, now let's move on to the second feature we wanted to implement. If you remember, we tried to implement a pieces counter in our code. And in order to do this, we used the combination of a blink and the CTU. So let's define all the variables that we need. We had a time specified that we called piece production time of type time, and it was 1 second. Then we created our blink function block. Remember that if you do not have the blink in your project, you should import it in the library. So I will do this by going in the library, clicking add library and searching for the blink. Wait a second. After a while, codesys has found my blink in the util library. I press OK, I import my library, and right now I'm able to define a blink function block. So I will call this blink piece production of type blink. So let's start by implementing this. Let's go down here and add a comment. Let's say this is the piece counting part of the code. So right now I should call my blink function block. I can press F2 in order to search my blink function block within all the code and insert automatically the function block call. So right now I shall click right here and write blink, and here you can see my blink. I double click on it, and here I have my function block call. The enable input of my blink function block should be set to the machine running variable, since we should be counting pieces only when the machine is running. The time low should be equal to the piece production time over 2, and the same goes for the time high. Okay, let's place all this in a better order by doing this, by starting new paragraphs. Okay, and let's now see if the machine is running. If our blink is actually generating a periodical signal on its output out. When you are in an online view, you can look at the input and output of the function blocks by clicking this plus and correspondence of a function block. So let's start our machine with these 3 conditions. Ctrl F7. Now machine running is true, and as we can see, the output of the blink is going from true to false with a period of 1 second. Okay, this is great. Let's go offline, and now let's implement the CTU that we used before. So we define a counter for the pieces. The type of the variable is CTU, and we also define a variable to keep track of the pieces, so a pieces number variable. The type is a word. So in order to do this, we should go down here, press F2 once again, and search for our counter. Here we have this counter pieces. Click OK. Here we have our function block already set in a good way. So the CU input of the counter pieces should be actually the out of the blink, since the CU will be used to increase the counter at each rising edge of this variable. So we will write right here blink piece production dot out. The reset variable, as we have seen before, should be not the machine running, meaning that we should reset the counter when the machine is not running. So we could write not machine running. The PV actually doesn't matter for our application, so we can write 0. We are not using the Q output, and we can finally place the CV variable onto the pieces number variable. Okay, let's go on and build. We have no errors. We can go online, download the program once again, start the PLC, and now let's take a look at the value of the pieces number. So let's start the machine, Ctrl F7, and after 2 seconds we should see this value increasing once every second. So this is working. Let's try to turn off the machine by, for example, opening the safety barriers. Press Ctrl F7, and as you can see, the pieces number has become 0, just when the machine running variable became false. So we can see that this is working. In structured text, you're able to build code with much more freedom. It is much compact, but I guess that if you have never programmed a system with a textual language, it can be quite tricky the first time. So I encourage you to try and try again to start practicing with this language, because in the long run, learning how to use structured text will be a great plus, a great way to improve your efficiency in coding and developing software for your PLC machines. So here we are, we have done this. This program is doing exactly the same things that the ladder diagram program was doing. So in the next few videos I will teach you some other languages of the IEC 611313 standard, and after those we will start also to see many exercises, and in most of the exercises I will keep presenting my solution that will almost always be implemented in a structured text language. This is done. I will do this also to help you to understand all the mechanisms all the way to write quality code in structured text, and I hope that this will be helpful to you. In this lesson we will look into another language from the IEC 611313 standard, the function block diagram. This language is a graphical language that is very similar to the ladder diagram language. So, in order to carry out our lesson on FBD, we will start from the knowledge we already have on the ladder diagram. And in particular, we will try to implement the program we did a few videos ago in the ladder diagram video. So, let's start by that project that we already did, that I called project 1, and from that let's create another POU, a program. Let's call it PLC underscore PRG underscore FBD, and the implementation language should be FBD. Now let's open both both POUs in order to switch from one another and to see what we need to do. First of all, let's copy all the variables from the PLC PRG POU that we created. So I will copy them and paste them right here. If you don't have the program, pause the video and copy these variables. They are the same that we used also in the structured text video and so on. So FBD works in the same way as ladder diagram. There are different networks that work as lines of code, graphical lines of codes, and there are a few differences, but the basic concept of FBD is to use block schemes to carry out sequences of operations in different networks. So we will try to convert this program into the FBD in FBD, and we will see what are the main differences. So let's go line by line. Here we have a contact and a jump. So this first line of code means that we should carry out a jump if the variable machine ready is equal to true. So in order to do this, you should insert right here in the FBD code and assign a jump right here. Let's drag it over here, and as you can see, some question marks pop up. This question mark on the right should refer to the name of the label. It was called the start of machine cycle, so let's write this here. Start of machine cycle, and on the left we need the name of the variable that will carry out the jump. That was machine ready. Okay, so moving on, we have this line of code saying that we need to first check if the low velocity is different from 0. Then if it is, we should assign the low velocity to the machine velocity and set the machine ready variable. So let's insert right here a new network, and in a similar way that we already used in ladder diagram, we can add a few box and math operators. For instance, an not equal operator right here. As you can see, right here we can define the variables that we need to look into. So we could say low velocity and 0. So if low velocity is not equal to 0, we should do something right here and carry on some connections. So in a similar manner from what we did in ladder diagram, we can insert a move block right here, and here you go, box with ENO right here, and this should be a move block. This move block should set the low velocity into the machine velocity variable, and then we should also set this machine ready variable to true. And in order to do this, we could, since we do not have contacts and coil in FBD, we could use another move block right here. A move block setting the value true to our machine ready variable. Okay, so we carried out these two lines. In here we should, if machine is not ready, we should carry out another jump. So let's insert a network right here. And let's place right here a jump. A jump to the label we called end of machine cycle. And the variable should be not machine ready. So let's write machine ready right here. And then you may right click right here on this point and click on negation. As you can see, a white circle will appear right here, and this white circle means that the negated variable is used for the operation. So in this case, the jump will be carried out if machine ready is not equal to true. So if machine ready is false. Okay, so let's move on. We have this other line that has the start of machine cycle label. So let's insert a network below and add a label called start of machine cycle. And in this program we should carry out a few operations. So as you can see here, we have a series of many conditions, 5 to be precise. Safety barriers closed, emergency OK, start button, not stop button, and machine velocity different from 0. In order to carry out a series operation in FBD, you should use an AND operator that is similar to what we did in the structured text language. So, in order to do this, you could simply use, or you can insert an empty box and write AND, or drag out one of these two, this AND, on the right toolbox. So let's drag it out. I selected the one with 3 inputs, but actually, as you can see, we need 5 inputs. So I can just right click on the AND function block, on the AND block, this is not a function block, and click on append input. Okay, so right now we have 5 inputs. So our 5 inputs will be this ones: safety barriers closed, right here, the barriers closed, emergency OK, start button. Here we should have the stop but the not stop button condition. So stop button should be equal to false. So let's write right here stop button, and let's right click over here and insert a negation. Okay. The last condition is that machine velocities should be not equal to 0. So let's delete these question marks and drag a not equal operator from the right toolbox over here. And this not equal operator should be given by the machine velocity not equal to 0. Okay, so the output of this series should be the input of RTON. So let's drag a box right here with the name timer machine startup. That is the name of our TON. We need to set the machine startup time in the PT variable. Machine startup time. Let's delete the ET question marks, and right here we should set the machine velocity, machine running variable to true. So let's do as we did before by inserting a move block right here. So let's copy an existing move, Ctrl C and Ctrl V, and I should copy true in our machine running. Okay, so we carried out the conversion of this line of code that is by far maybe the most complicated one we had in our original ladder diagram program. Let's go to the next one. As we can see right here, we have a parallel condition between three Boolean variables, and if you remember from our structured text lesson, a parallel operation is the same as saying that we are carrying out an OR operation. So we could drag the OR function from the right toolbar. We need only 3 input, and these inputs are, we should have safety barrier closed, negated. So let's right click here and insert a negation. The other condition to stop the machine is to have the emergency OK equal to false. So let's write this here and add a negation. And the last condition is the stop button. So if any of this is true, we should write machine running equal to false. So let's copy this move we had over here, and let's write false right here. Okay, we are almost done. We need to carry out these 2 operations to set the velocity of our machine according to the buttons being pressed. So let's insert 2 networks over here, and as before we have a series over here, and this means that we need an AND operation. Let's go to Boolean operation and let's drag the AND with 2 inputs. So over there we need the low velocity button, and down here we need the high velocity button with a negation. If this condition is true, we should carry out another move, and we should move low velocity into machine velocity. Low velocity into machine velocity. Okay, and right now, given that the fact that this line of code is very similar to the previous one, we could simply copy and paste, Ctrl C and Ctrl V, and then carry out some modifications. So we should invert the negations over here, so I could simply click on the white circle and press delete. Oh, sorry, this didn't work. I click and press delete. No, sorry, you should right click and press negation again. So let's invert the negations by right clicking and pressing the negation button. So right now we need a high velocity button and not low velocity button, and the move should be about the high velocity. Okay, we are almost done. We just need 2 more lines of code, and we first add this one about the blink and the count and the CTU, and this will be fairly similar to the one that we did in ladder diagram. So let's insert a box that will be our blink piece production, Let's write this over here. And in series of the blink we have the counter, so let's also add right here a box, and the box should be our counter pieces. Let's delete all the question marks, and right now we should fill the variables in the same way as we did in our ladder diagram program. So we have machine running over here to enable the blink, the time that was called piece production time over 2 divided by 2, and here again we had 0 in our PV input, and the reset was the machine running variable with a negation. So let's insert it, right click over here and negate this. And the last thing we needed to do is to set the pieces number equal to the CV output of the CPU. Okay, we are almost done. We just need a last line with a label and a machine cycle. So let's right click, insert label, end of machine cycle. Okay, we have carried out this program in FBD. So let's now open the two programs side by side and let's compare what are the differences between the two languages. First of all, we see that the contexts are now replaced by simply the name of the variable. We have seen that we have no longer the set and reset coils, so we carried out the same operation with the move. We also saw the negation, that is the operation to negate any input or output that in ladder diagram we carried out using negated context. And the most important difference is mainly that in function block diagram everything works with blocks, and there is no series or parallel of contacts, and you should use AND or OR operations. Other than that, you can see that the overall program is quite similar to the one we did in ladder diagram. These two languages are very commonly used, and they work in a very similar way. So now, in order to try this program, let's edit this call in our task configuration. So we don't want to call the ladder diagram program but our FBD program by renaming the task call. Let's go online and run a few tests to see if everything is working properly. I press start. Let's start the machine with the same operation that we did before. After 2 seconds, the machine running has become true. And right now, the CPU is counting the pieces. Let's try to remove the emergency OK. And the machine is now stopped. Let's try to change the velocity using the buttons. And the velocity has changed. So everything works the same way as before. We've seen this language that is very similar to ladder diagram. In the next video we will see a language that is not part of the IEC 611313 standard, but is still implemented in codesys. The name of the language is CFC. It's very similar again to FBD and ladder diagram. There are some differences, and we will see this in the next video. In this lesson we will see another language, the CFC or Continuous Function Chart. This is a language that is not part of the IEC 611-313 standard. It is somehow similar to FBD, so in order to explore it we will start from the program we already developed for the ladder diagram implementation and FBD over here. So in order to, let's create right now as before another POU by right-clicking on application POU program. Let's call this one PLC_PRG_CFC, and the implementation language should be CFC. Let's add it and let's copy the variables from the POU we already developed. If you don't have the POU, simply pause the video and take your time to write them in your declaration of the program. Okay. So, how does CFC work? It is a language based on the block schemes in the same way as FBD is. The main difference is that we no longer have networks, but we have a blank 2D screen where we can place our blocks wherever we want. The execution order is decided by a little green number that is placed in the corner of boxes that we'll see. So, let's try to implement these lines of code one by one, and let's try to see all the differences. So, as before, the first line of code is a jump. So, starting from our program, we could simply add the jump from the toolbox on your right. Over here, you will see the jump, and this is the number that I told you about. In order to carry out the jump according to a variable, you should insert an input. As you can see, we can move all these objects wherever we want on the screen, and to connect them you should simply drag an arrow from one point to another. So we need to connect an input to a jump. The input should be machine ready, as we already did, and the jump should be what we called start of machine cycle. Okay, so let's move to the next line that we carried out in FBD. So first of all, we have a not equal operation. We can add a box over here by dragging it down here, not equal, and we should add two inputs for our not equal. So let's place one here and one here by copying and paste it. The first one should be low velocity and the second one should be 0, low velocity. Let's move it back quite a little bit in order to be easier to read. And then carry out the connections from 0 to this second input and from low velocity to the first input. Okay, so moving on, we need to have a move and another move. So in order to do this, we simply need to add a box over here. Let's add a box and write move in this place, and in order to have the enable and enable output pins, we should right click on the move box and click on en/eno. Let's carry out this connection over here, and then we should add an input over here and an output over there. So I will create an input here. This input should be low velocity. And an output over here should be machine velocity. Let's carry out the connection. And we also need another move, so let's copy and paste it over here. And let's carry out this connection. This move should set true into the machine ready variable. So let's place an input and an output. Here I will write true, and here I will write machine ready. And let's carry out the connection. As you can see, our CFC editor some kind of messed up the order of the function block, of the block calls. In order to manually change the order of execution of our blocks, you could right click into one block and go into execution order. You can either send this block to the front, meaning it will be executed as the first one, send it to the back, meaning that it will be executed as the last one, move it up in the execution order, move it down, or set the execution order to the number you desire. You could also carry out an automatic ordering by the data flow, meaning from according to how you placed your blocks in the CFC window, and this will be carried out from top to bottom and from left to right, or by topology, meaning that it will depend on the actual type of blocks that is being called. And if I click on order by data flow, you can see that it has already gained an order that we would like. As you can see, the first one has the number 0, then we have 1 over here, 2 over here, 3 over here, 4 and 5. So my suggestion, my personal suggestion, is to first carry out your programming in as you wish. Then you should order the blocks in with some kind of structure from top to bottom and from left to right. And after that, I suggest you to simply click execution order and order by data flow, because it could be quite painful to manually change the order of all the blocks. So now moving on, our third line of code is such that if machine ready is equal to false, we should go to the end of machine cycle. So we could simply copy this, since it is very similar, and paste it. Move it down here, and here we have an end of machine cycle label where we want to jump to, and the only thing that we need to carry out is a negation by clicking on this segment and clicking negate. Okay, so now let's move on to the following line. Here we have first of all an end operation. So again, as we did in FBD, we will in the box over here there will be an end, and in order to add some inputs, you should right click on the block and go into add input. For this block we need 5 inputs, so I will do this 2 more times. Okay, so our first condition is safety barriers closed, and so on, all the conditions that we are already seen. So first we will need 4 inputs over here, so I will place them by copying and pasting. 3 and 4. Let's also carry out the connection. Our first condition is emergency. Okay. Then we have the safety barriers closed. Then we have here the start button. And over here the stop button. And the stop button condition should be negated. So once again, let's click over here and negate the condition. Then on this pin we should add a not equal operation. So let's add over here a block. Let's write NE on the question. And then insert again 2 inputs. One over here and one over here. And this not equal should be between the machine velocity variable and 0. Okay, and then this not equal output pin should be dragged into the end input pin. Okay, moving on. Right now we should attach this output to the TON. So let's insert over here a box, and this box should have the name of our timer. So we call this timer, sorry, what was the name again? The name was timer machine startup. So first of all we should right here a TON, and and the name of the TON should be timer machine startup. Okay, this is our TON. Let's drag this output into the input of the TON, and we also need another input over here connected to the PT input, and this variable should be the machine startup time. Then this Q output should enable a move operation that will set machine running to true. So let's move back here. Let's copy and paste a move from an existing block. Let's place it over here. Let's place an input and an output over here and carry out the connections. We should write true into the machine running variable. Okay, so this again was the probably the most complicated line of code we had in our original program. And we can go down here and add some more lines. We have the deactivation condition, that is an OR operation that will enable a move. So let's create a box. If it seems like to you that we have run out of space, you can simply drag a box and go down. As you can see, the CFC page will become larger. And here we have an OR operator that should be among 3 inputs. So let's create it and copy a few inputs. Let's place them a little back. Let's carry out the connection, and here we should have emergency OK. That should be negated. Right click, negate. Safety barriers closed. That should be again negated. And the last one was the stop button. Okay, so the OR of these three variables should enable a move operation. So let's copy and paste maybe all of this. Copy and paste. Sorry, you can carry out a multiple selection by holding your control button on your keyboard. I've dragged this here, and the only modification that is needed is to write false over here. Okay, so moving on, we just need to implement these 2 lines of code regarding the velocity change with the 2 buttons. So first of all, we should carry out an AND operation. So again, I will place a box over here and drag it down. Here we have our AND operation with 2 inputs, 1 and 2. Copy and paste them. The first one should be the low velocity button, and the second one should be the high velocity button. Let's drag them a little left. Let's carry out the connection and insert a negation over here. Okay, this should again enable a move, so I will copy this move from over here and place it right where we need it, and change the values. So this should be low velocity. That should go into machine velocity. Once again, the line concerning the high velocity button is quite similar, so I could simply copy all this code and paste it. So press Ctrl C and Ctrl V, and I will drag it down a bit. The only thing I need to change here is the negation. I remove the negation from the high velocity button and I place it onto the low velocity button. And then I also need to change the high velocity over here. Okay, we are almost done. We just need to add this line of code. So first of all, we need our blink box. So create an empty box, drag it down here, and this should be a blink. And the name should be our blink piece production. Let's also add the CTU over here by placing a box writing over here CTU, and the name of the CTU was our counter pieces. Okay, I will drag it a little bit right. We will need this connection, and we'll need quite a few inputs. One over here. I will copy and paste and place them all over the place. Okay, and I will carry out all the connections. So our enable signals should be the machine running variable. I will drag them both quite a bit to the left. This should be our time divided by 2. PS production time divided by 2. And the same should happen in the time high. Ctrl C and Ctrl V. The reset should be the negation of our machine running variable. So we will write machine running, right click over here and negate. And the PV variable should be equal to 0. Then we just need an output that should be placed here, connected to the CV, and that should be set equal to the pieces number variable. Okay, so we didn't manage the labels, so I just need to add a label over here. This label should be called start of machine cycle, and I should place another label at the end of everything by dragging it over here, called end of machine cycle. As you can see, the labels in CFC are not directly connected to a line of code. They are instead linked to the number that we have right here. So by jumping to a label, you will simply jump to the corresponding number of execution or in the execution order. So, as you can see, all the numbers right now are messed up, so we should just right click wherever we want and order by data flow. As you can see right now, everything should be fine. Let's see, we have 0, 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, everything seems good. So, I suggest you to, if you are using CFC, I suggest you to write the code in an ordered fashion. Right click and order by data flow, and then when the flow of the execution order is set, then you are able to move every line of code wherever you want and place them on your screen according to what you prefer. But first of all, I really suggest you to place that in an ordered fashion in order to be able to carry out this operation that will simplify your life quite a bit. So let's see how it works and what are the differences between CFC and FBD. Well, the logic of all the code is quite the same, because as you can see, it is quite similar to what we already did in CFC, in FBD, sorry, and all the lines of code are quite the same. The main difference is given by the execution order, and also you have to add all this input and output pins every time you want to add an input and out to carry out a connection to a box. You can also add a few comments using the comment operation, the comment object, where you can say add some comments near your line of code. Starting the machine, maybe over here. I could write another comment over here. Stopping the machine, and so on. There are many things you can do, and this is it. Let's try this by going online. First of all, I need to change the task call to the CFC one. Let's build the program. Okay, we have no errors, Let's go online, log in with a download, and let's start. So I will check the variables only to see if everything is going correctly. I will carry out the start of the machine in the same way that we did in the latest project. After 2 seconds, machine running has become true and the pieces are being counted. Let's remove the safety barriers, close the condition in order to stop the machine. Yes, it works. And let's also see if the buttons for the velocity work. Yes, machine velocity has become 1000 and now it's become 200 again. So it works in the same way of all the programs that we have already seen. In my opinion, CFC is quite tricky because there is a lot of work in ordering your code schemes and your flow of execution, and you also have to insert manually input and output every time, so writing code could become quite slower with respect to other languages. But sometimes you may see that this language is used in many applications. In this lesson we will carry out an exercise, the first exercise of the course, that is about the control of a simplified elevator. In the attachment of this lesson you will find a compressed folder containing 2 files, a project file and a project archive file. In order to carry out this exercise, I suggest you to first try to open the project file that contains the overall environment for the development of this exercise, and if you encounter some issues or some errors with the opening of the project file, that can be given by the fact that you may have a different codesys version with respect to my own, I suggest you to open the project archive file. This is the project that you will find, that you will have in the attachment. Every exercise or example that I will provide you will come with a set of global variables right here that are the variables of the process that you need to interact with, and mainly they will be input for you that you will read from the process, and the others will be outputs that you will write in order to control the process. Everything will come with a visualization that will be quite useful to see how the application is running, to have a visual feedback of your code, and to have an actual feeling of the simulated process. In the project there will also be a simulation program that you will not need to use to touch, and this is where I wrote my code to simulate the process. So in this project you will have to control this elevator. You will have these 10 buttons that the user should be able to press in order to go to a certain floor. You will have this display bar that will show you where the elevator is, and this text box will tell you what is the current floor. The variables with which you can interact are this. We have right here an array of 11 Boolean variables. We have never seen arrays before, or maybe you have on different projects on different languages, but you should know that arrays are a set of variables, and they are numbered, in this case, from 0 to 10. So if I say the floor buttons numbered 0, I would refer to a certain Boolean variable. Instead, if I refer to floor buttons number 10, I will refer to another. Respectively, they are the Boolean variable that tell you if these buttons are being pressed. Then you have this udint variables that tells you what is the current elevator floor. We have an on floor input that tells you if the elevator is currently aligned with the floor. Then to interact with the elevator, your actuators will be a command to move the elevator up and a command to move the elevator down. Okay, so in this project right now I have already implemented my solution. So I will go online and let you show you what I expect from this project. Now it's compiling and downloading. I will start the CPU, and here I'm online with the visualization. If I click, for instance, the 5 button, I would want the elevator to go to the 5th floor. If I click the 10th, I will want it to go to the 10th floor, and so on. This is a very simple application. It is very simplified because, for instance, if I click another button, I would want the elevator to take in charge this new request and not to carry out the one that it was doing before. So this is a very simplified elevator. There is no management of the series of calls that are coming from the floors. Here you have only the panel inside the elevator, so there are no movement of the doors, and it is very simplified. So I will now go offline. I will delete my implementation and I will carry out and create a new POU in order to show you how to do this. I will first carry out the implementation in structured text, then I will do the same, carry out the same program in ladder diagram. Okay, so let's create a POU that I will call again PLC_PRG, and this is a program, and now it's empty. Okay, so let's open also the global variables. In codesys you can open many windows in the same at the same time by carrying out the tab, by clicking and dragging the tab and place it anywhere you want on the screen. It is, as you can see, this command buttons appear when I'm dragging a window. If I place it in a certain position, I could split the screen between my windows, and this is quite useful sometimes, like this. So we can write code while looking at these variables. Okay, so what should we do right now? Well, we should, at any cycle of the PLC, check if any button is being pressed. So how can we do this? The really naive way should be to check if floor button number 0 is being pressed, if floor buttons number 1 is being pressed, and so on. Then, given if one of these is being pressed, we should register what is the number that is being pressed. So we should have a variable that we may call requested floor. Let's say that is udint variable just to be consistent with the current elevator floor type. And in a very naive way, we should carry out a if floor buttons of 0, then requested floor is equal to 0. If floor buttons is 1 is true, requested floor should be equal to 1. But as you can see, we are writing the same code all over again. Well, if you know a little bit of computer science, you may know where I'm going with this. There is a simple instruction, a simple tool that is called a for cycle. A for cycle is a way to carry out an operation for a certain numbers of times. In order to create a for cycle, we should have an index variable, an index for the for cycle. Now you will see what I mean. I will create an index variable, another uint variable, and I will write right here, I will remove this part later on, and I will write for this index going from 0 to 10. This is the syntax of for loops in structured text. So for this index going from 0 to 10, do this, do. If I press enter, you will see that an end for is carried out. So the line of code that I will carry out right here will be done each time, and a certain amount of time for this index variable. This means that these lines will be executed with index equal to 0, they will be executed with index equal to 1 until index is equal to 10. They will be executed for index equal to 10, and then the code will move on to the next lines. So what we could do is the following. We could write right here, if for buttons of index, then the requested floor should be equal to index. In this way we are scanning all the buttons to see if any one of those is being pressed, and we are setting our requested floor to this index, to the one that is being pressed. Right now we are not managing the condition in which many buttons are being pressed at the same time. With this implementation, if many of them are being pressed at the same time, we will choose the smallest one. Oh, sorry, we will choose the biggest one, I'm sorry. So, moving on, these lines could be deleted, and I will call this part the floor buttons scan. Okay, so in the following lines we should handle the movement of the elevator, meaning we will write a comment called elevator movement management, and we're supposed to have at this point in the code a requested floor with a number in this. So we should compare this requested floor with the current elevator floor in order to carry out the movement. So let's check all the possibilities. Well, if the current elevator floor is smaller than the requested floor, then we should move up. And in order to move up, we should set this command elevator up to true and the command elevator down to false. So let's write here another command, move up, and this is command elevator up equal to true and command elevator down equal to false. Semicolon. Okay, this will handle if the requested floor is above the current elevator floor. If instead it is above, meaning that we have to move down, I will write right here another comment, move down. We'll write right here an else if the current elevator floor is bigger than the requested floor, then we should move down, meaning that the command elevator up should now be false, and the command elevator down should now be true. Okay. This was requested floor. Now something is still missing, and I will see you by going online and testing this code. Let's log in with the download. Let's open the visualization, close the global variables, and press play. Let's go, for instance, to the 5th floor. As you can see, we are not managing the stopping condition, so the elevator will keep going from the 4th to the 5th, 6th floor. If I press the 9th floor, for instance, right now we are having the same issue. So we should manage this. Let's go offline and also add another condition. Here we could simply add another else, but right now we should also take into account this global variable on floor. So we should stop the elevator if the current elevator floor is equal to the requested floor, and we have this on floor, so we stop at the right position. So else if the current elevator floor is equal to the requested floor, and we have this on floor sensor equal to true and on floor, then in this case we should simply set this variable to false, both of them. So let's copy them and paste them right here and set them both to false. Okay, let's go online. Let's build and go online. Let's carry out a download again. Let's go into the visualization and let's click, for instance, the 7th button. As you can see, right now it is working flawlessly. It is going to the right floor and stopping there. We could also open in the separate tab the value of the variables and see how the command elevator up and down are reacting to our button pressing. So as you can see, when we arrive to the correct floor, both of them become false, and the floor button and the floor sensor is true. Okay, this is fine. We managed to do this in structured text. Let's now try to do this in ladder diagram. So I will change the name of this POU. Let's call it PLC underscore PRG underscore ST. Here, when we rename a POU, codesys will ask us if we want to carry out the so-called refactoring, automatic refactoring, meaning that it will check in all the project if we desire the name. It will change the name of our entity and change it all over the project. If I click yes, here I will see this PLC underscore PRG changing name as well as any call in the code of this program. But right now I don't want this, so I will click no, and I will create another POU called again PLC underscore PRG, and this will be a POU implemented in ladder diagram. Okay, so let's try to carry out the same stuff with our ladder diagram code. So let's open this in a parallel window right here in order to see what we did. And we should declare the same variables, so I will simply copy them and paste them in the new program. So unfortunately we don't have a feature in codesys to carry out a for loop. The only way to carry out this for loop is to use jump and labels that we have already seen. So we should carry out this operation in the following way. Let's create a few networks right here. And we should do the following. At the start of the program, just one thing that I didn't tell you. Of course, all of this is happening in the same cycle. We could do this in ladder by simply having an index that we increment at each PLC cycle and check the corresponding floor. But what we want to do is to carry out all of this in the same cycle. So, I was saying, the first thing that I will do, that is the same thing that is done at the beginning of the for loop, is to set the index equal to 0. So, in order to do this, I will add right here a box. That will be a move box. Move. And then we'll move 0 into the index. If we don't have this place where we can write, just drag an assignment right here. Oh no, sorry, you should have the box with EN and O inserted. So let's delete this. Place a box with EN and O. Okay, that's right. And move. And we should delete this contact because we want to do this regardless of any condition. So we will write right here 0 and requested index. Right now we are setting the index equal to 0. Okay. So right here we should check if the floor buttons of index, so let's place right here a contact, floor buttons of index. If this is true, then we should carry out another move and move the index into the requested floor. Let's place again a box with EN and O, or simply we could copy the move. So let's click Ctrl C and Ctrl V. And we should move the index into the requested floor. Okay. So right here we should increment the index. So let's write, we could simply add a met operator, an add operator, we could drag it right here, remove the enable contact, and let's say that index plus 1 will be the new value of index. This is how an arithmetic math operator works. We are adding this. Then we should check if the loop has ended. If it hasn't, we should jump back to this line. So we should check if the value of index is still lower or equal to 10. So let's drag this box del LE, meaning lower or equal, less or equal, here. Let's again remove the enable contact, and if index is lower or equal to 10, we should jump back to this line. So we should add right here a label called start of for cycle, for instance, and right here we should add a jump. Let's, by clicking on this arrow, and right here, start of for cycle. Okay, so what will happen that these two operations will be carried out 11 times, because they're from 0 to 10. 11 times. You can also see that we have 11 buttons. They will be carried out 11 times, and after that it will move on to the following lines of code. You must be very cautious with the use of jumps in ladder diagram to previous lines of codes, because if you don't write a consistent condition right here, you might have you might be in a condition in which the program will be stuck in these lines forever. This means that the program will never end a PLC cycle, and on a real system you will get into real troubles, and maybe a watchdog mechanism will stop the CPU. So let's move on and have some new networks down here. I will now carry out these lines of code. So let's check this and add right here our map operators. So if the current elevator floor is lower than the requested floor, this is carried out with LT lower than LT, no enable signal, and so we will have current elevator floor. Let's remove the global variable repository, and the requested floor. If this happens, what should we do? We should set the command elevator up to true and the command elevator down to false. So we have a set coil to command elevator up and the reset coil to command elevator down. I will remove this. So let's click right here. Let's click right here and select the insert branch, that we create this branch right here, and add a reset coil for command elevator down. Okay, this is great. And in order to carry this other line, we should simply copy and paste this network. Let's copy and paste this. We shouldn't have an LT, but instead we should have a GT greater than. So let's write a GT over here, and as you can see, the block changes. And we should also invert these two coils. So the command elevator down will be set, and the command elevator up will be reset. Okay, we are almost done. Let's paste the network here again. So right now we should check if the current elevator floor is equal to the requested floor. So here we should have an EQ operator, meaning right here the equal operator. So let's write EQ, and then we should reset all both commands. So let's delete this and add a reset coil for the command elevator up as well. We should also add this condition, and since we are doing an AND operation, it is the same as doing a series operation in ladder diagram. So let's put a contact right here. Click here and place a contact with the on floor condition. Okay, We are done right now. Let's build our solution. As you can see, the name of our structured text POU has become gray, and this is due to the fact that it is not scheduled and it is not being used within the program, within the PLC software. Instead, this one has become blue because it has been recently added. So, let's try this. Let's go online and carry out a download. Okay, let's go into the visualization and try this out. Clicked on the 5 button and it has reached the floor correctly. Let's move to the 9th. Everything good. Let's do a change while it's moving. Okay, it is running again as we desired. So, as you can see, let's now go online and compare the two POUs that we wrote. As you can see, in this occasion, the ladder diagram is already less intuitive in my opinion, meaning that here you have these 4 lines of codes that are not very easy to write to carry out a simple for loop. Then we have these 3 lines that are quite simple, but I mean they are also simple in my opinion in the structured text. In real machines you will have tons of lines of codes and you will have to handle many situations, so the length of code will be much bigger. So I will suggest you to use mainly structured text language for many parts of the machine code. You could still use ladder diagram for simple things, but as you can see, structured text can be more compact and direct. In this video we will talk about state machines, and now they will help us in programming PLC applications. So far, we have seen a sequential kind of programming, quite simple and direct. In each language we had some code executed at each PLC cycle, in which different conditions were checked sequentially to generate certain actions accordingly. This type of programming is not very suitable for the management of sequences of operations, which is one of the classic control scenarios for a PLC. This structure leads to messy, confusing, difficult to read and to maintain code. As complexity increases, managing sequences of operations in this way is not sustainable. Therefore, we introduce a different programming pattern, the state machine. The state machine relies on dividing the code into different portions called states. The portion of code corresponding to a state is executed only if the program is in that state. The transition from one state to another occurs through the specified condition, causing transition from state to state. Using a state machine to manage sequences of operations brings greater structure, order and clarity on the sequence of operation that must take place. The state machine is at the center of PLC programming and it is used continuously by professionals in the field. Let's take an example of an application and realization of a state machine. The application is the management of a simple one-way level crossing. We have 2 sensors, sensor A and sensor B, which testify the presence of a train at their position. We have an actuator which controls the lowering and raising of a group of safety barriers. We start from an initial state, which we will call state 1, in which there is no train and therefore the action is to keep the barriers raised. As a condition for the transition to a subsequent state, that means that a train is incoming, the transition will be the activation of a sensor A. In the next state, which we will call state 2, it will be necessary to lower the barriers because a train is arriving. Next, we will have to wait for the activation of sensor B, which will testify that the train is passing in front of sensor B. In the next state, that we will call state 3, it will be necessary to continue to keep the barriers lowered, because the train is still near the level crossing. To be sure that the train has passed, you will have to wait for the deactivation of sensor B. In this case, you will no longer have a train in the level crossing, and you can go back to state 1, waiting for a new train with the barriers raised. The implementation of this state machine makes the flow of the code very clear. State machines are easily developed in the SFC language, which is a language developed specifically for this pattern, and it is based on the construction of block diagrams that closely resemble the flow of a state machine. However, state machines can also be developed in any other language of the standard. In the next videos, we will see how the SFC language works and how to create state machines in SFC, ladder diagram, and structured text. In this lesson, we will learn about the SFC language. As I told you, the SFC language is based on creating state machines, and we will approach this language with a practical example. So I suggest you to download the files in the attachment of this lesson, and you will see a project that contains, as always, a set of global variables, a simulation, POU, and a visualization. And this application is very similar to the one I presented you in the slides, and this is about a two-way level crossing of a train. So let's go online and I will show you all the what the application is about. So in this application, you can see that a train may come from above or from below, and there are two sensors, sensor A and sensor B, and the purpose of this application is to control in the right way the barriers. Right now there is no program running, the PLC_PRG is empty, and as you can see, the barriers are always up. So the purpose of our program should be to manage the barriers correctly and to detect from which side the train is coming. And in order to do this, we will use the SFC language and create a state machine. So let's go offline. I will show you what are the global variables. They're very simple. We just have the sensor A and sensor B, and the command for the barriers. And if this boolean variable is false, the barriers will be raised, just as we have seen, and if it is true, they will be lowered. So let's see how the SFC language works. The SFC language is about vertical block diagrams representing states. So whenever you see a light blue rectangle, this is a state. Then there are transitions between states. In the basic program that you see, you will have just one state called init, a transition through, meaning that the transition has an always true condition, so it will always happen, and right there a jump back to the init state. So this program is actually always staying in the state. So the state machine, the SFC code, runs the content of the state, it evaluates the transition, and at the next PLC cycle it will again run the code of the state. So let's start from the command to create a state machine. So if I click right here on the state, right click, you can see that I can add a step transition either before or after. If I click after, as you can see, these two objects have been created. This is a transition, so here you need to specify a Boolean kind of condition. You could specify directly a Boolean variable or either any condition regarding any variable. For example, I could say a certain number must be equal to 0. All these transitions are accepted. And over here I have another step. So let's first think about the step that we need for our train management application. So as you can see, also the inner state looks a little bit different. There are two rectangles in it. This is what defines an initial state. So if I, for instance, click right here, right click and select any step, you will see that this aspect will be on the step 0. So let's make this one an init step, and let's say that this is the state where we are waiting for the train. So I will just write over here, waiting for train. Okay. Then, in order to, let's create the transitions to other states. So, starting from this state, we could have two possibilities. We are waiting for a train. We could either read the sensor A equal to true or the sensor B equal to true. This information will tell you if the train is coming from above or from below. So we should have two transitions from this state. In order to do this, you can simply right-click on the state, right-click on the transition, and select the Insert Branch Right. And in this way, this structure has been created. So, right here we have this starting state and two possible transitions. If none of this is true, if no transition is true, the state will remain this one. If one of these transitions becomes true, the state flow will jump to the next state. So, as you can see, here we have a state, here we don't. So let's add a state below this transition by right-clicking here and clicking Insert Step Transition after. So let's try to create a structure to our state machine. If we read the sensor A equal to true, then we should go in another state where we know that a train is coming from above and it is on the A position. So let's try train from above A. Okay. Instead, if we read the sensor B, we will go to another state telling us that the train from below is on B position. Okay, the names of the states are totally arbitrary. They don't matter at all in order for the program to work. So, moving on, what should happen? Let's follow this branch from the left branch. So the first thing that happens, we read the sensor A. Then, in order to be sure that the train is passing, we need to wait for the sensor B to become true. So, over here, let's add another step transition after. And let's say that this transition is given by sensor B. Okay. And we are going to another state called train from above, that is now in the presence of sensor B. Okay, then in order for the train to be outside the level crossing and for us to be able to lower again the barriers, we just need to see if the sensor B has been deactivated again. So we will so the sequence is A, B, not B. So I will just write over here, not sensor B. Oh, sorry, I wrote this wrong. Not sensor B. Okay, and I will delete this step and this transition. And over here, I will allow a jump to the initial state. And this will be the initial state that is waiting for train. So on this branch, what will happen is we wait for sensor A, we wait for sensor B, we wait for not sensor B, and then we are back waiting for new train. On the other branch, it should work on the same way. So first we read the sensor B, then we need to read the sensor A, and then not sensor A to be sure that the train is outside of the level crossing. So here we write sensor A. We insert a step transition after this. We will call this state train from below A. That is because in the state the train is right near the sensor A. And in order for us to be sure that there is no more train, we will write over here not sensor A. Okay, so right now we have a state machine, but in the state machine we are not actually doing anything. We are just changing states, but we are not interacting with the variables, with the actuators in particular. So what should we do now? So there are many ways to interact with variables using SFC. So this means to set the states, set the variables from the states. But before doing that, let's go online and see if the flow is working correctly. There is a nice visualization for the debugging system of SFC, and as you will see, when we go online, the state that the state machine is into will become blue. So I will just drag the visualization on the side of the screen, so we will see the state machine working. So train coming from above. Yes, it works fine on this branch. Let's wait for a train in the other direction. It is purely random the direction where the train comes from. And right now you can see how it works. On the right of the state you can see the time in which the flow has been in this state. And now you can see basically the logic behind the state machine. And right now we are not using the barriers. The barriers are not being used in any way. So in order to interact with variables, with Boolean variables specifically, you can right click on a state and you can simply enter and insert an action association. As action association are built this way. So you need to specify an operation over here. These operations are purely made for SFC, and over here we can specify the variable. These operations are called qualifiers, and most common qualifiers are the N qualifier, That means that the variables that we put here, for instance the command of the barriers, will be true if we are in the state, for the time in which we are in the state. Once we get out of the state, the command will be set to false. So this is useful to maintain a certain variable to a value only when inside the state. So, and we also have the S qualifier, meaning that this is a set qualifier. That means that as soon as we enter the state, we simply the variable will be set to true. And the opposite of this qualifier is the R qualifier, the reset, meaning that as soon as we enter the state, the variable will be set to false. So what we need to do right here would be to set an R qualifier for this operation, for this state on the command barriers, meaning that as soon as we are waiting for the train and there is no train incoming, we just have to raise the barriers. And then as soon as we sense a train, it means either in this state or in this state, we will need to set the variable. So I will insert an action association over here with set and also command barriers. And the same should be done over here as command barriers. And we should be good to go. Let's try to go online with a download. And by pressing start, we will see now the barriers working properly. You can also see the barriers coming through because they light the variable lights up in a blue fashion. So this works great, and we have built a simple state machine with 5 states in order to handle this simple process. But typically you may see that this just being able to set a single Boolean variable, or to interact only with Boolean variables, may be too restrictive for your applications. And typically there are also other possibilities for in order to have actions inside the states. For instance, you could add an implementation, an action connected to one state in another language. And the classical application of SFC regards the usage of structured text to write the code of what should happen inside the state. So for instance, if I just double click over here, codesys will ask me if I want to create an action for this state, and for this action, if I want to copy the reference from another action or copy the implementation of an action that I've already created for another step. So for now I will just click on copy reference because there is I didn't create any other action. And here I can create an action called train from above be active. If I click add, you will see that codesys will create this action in the PLC below the PLC PRG POU. And here I can write code in structured text that interacts with all the variables that the POU can see. So here, for instance, I could write command barriers equal to true or anything else, and this adds a lot of flexibility. And if the state machine is inside the state, it will call the action of the state once for each PLC cycle. So technically you have two alternatives. You can either use the actions, that is the action associations that are used right here, or you could write your implementation of the action in another language. So right now I will delete this. If you delete an action, you should also click on the state and go into the properties right here and delete the action. And right now you will see that the triangle that was over here has disappeared. And also you have another two tools for the SFC that are the entry and exit action. So you may also define, other than a simple action that runs cyclically when the state machine is in that state, you can add an entry action that will execute once when the state machine transitions to the state. And if you create an entry action, you will see in your state machine this E symbol over here. I will just press Ctrl Z to cancel what I did. And in the same way, you can add an exit action in order to have an action that takes place only once when the state machine is exiting from that state. And if you create an exit action here, you will see an X over here. Okay, so there is another tool that we didn't see, that is the parallel, meaning that you can diverge from a state, creating a set of parallel state machine running together. We won't see an application of the parallel in this course and in this application, but just know that this is possible. And in the next videos we will see how to create state machines in other languages that are not SFC, and mainly we will learn how to do them how to create them in structured text, and they will be very useful to create quality code in structured text and to create state machines. In the last video we have seen the SFC language, and we've seen that the language is totally based on creating state machines that are a quite useful pattern to handle sequences of operations. Right now we will see how to create state machines in other languages. Mainly, right now we'll see how we can write state machine code in structured text language. So we will start from the same example that we have already seen, the one of the level crossing and the train, and we will keep the code that we implemented in the ladder diagram language, and we will try to create a state machine with a new POU implemented in a structured text language. So let's create another POU. And let's call this PLC underscore PRG underscore ST, and the implementation language should be the structured text one. Okay, let's also change the call in the main task by right-clicking. With a slow click you can rename this entity over here, and let's write ST. So right now, if we build, you will see that the PLC underscore PRG becomes gray, since it is no longer being called, and we will call this POU instead. So for the purpose of this lesson, I will open both POUs in parallel like this. I suggest you to do the same, or just to look at me, so you can take care of all the similarities between the code. So, how can we create a state machine in the structured text language. The state machine itself is a way to divide code into states. So in this way, the code that corresponds to a state will only run if the machine is in that state. In order to do this in the inner structured text language, you need to use a variable to identify the state that you are into. So let's, for instance, create a variable. Let's call this machine state, and the type may be a uint type. Okay, so in order to divide code for different states, we could do something like this. I could simply say, like, if my machine state is equal to 0, for instance, then I should do something that corresponds to the state 0. For instance, I could write here a comment that my state 0 is the waiting for train state. And here I will need to write some code. Then I could say, okay, maybe instead, if the state machine is in another state, let's say that it is in state 1, machine state is equal to 1, then here I should run some code for the state 1. And according to some conditions that I will specify in the code of the state, I could handle some transitions. For example, I could write something like, if a certain Boolean variable, then change the state and carry out a transition. Machine state, let's set it equal to 1. Okay, this is good, this is a way to do it, but in this language there is a really useful instruction to carry out a sequence of conditional statements based only on one variable, and this instruction is called the case instruction. The syntax of the case instruction is this one. You should write case, the variable that you are looking into, of, and by pressing enter you will see that an end case operator will be put in a one line, and all the case statements will be here. So you need to write the value of this variable that you need to look into. For instance, I could say right here 0, colon, and here I could write some code for state 0. Again, here I could write 1 and say right over here a code for state 1, and so on. This is the same, works in the same way as a sequence of is, if, else if, else if, else if. So what should we do now? Let's try to build a state machine that carries out this operation that we did in the SFC language. So let's delete for now these comments, and I will start with the first state that we will use, that is the waiting for train state, and we would define that this is the state where machine state is equal to 0, state 0. So I will write right here a comment that this is the waiting for the train state. Okay, then in this state what should we do? We should lower the barriers. So in the code over here we could simply write the command of the barriers colon equal to false. This is what should be done in this state for the time that we are remaining in the state with the state machine. Then we should handle a transition to another state. So if the sensor A is detected, we should carry out a transition to another state. And transitions in state machines in structured text are done by setting a new value for the state variable. So, for instance, I could say that if we read a sensor A equal to true, we could write machine state equal to 1. So what will happen is that if on a cycle we are in state 0, we will detect sensor A, machine state will become 1, and then at the next PLC cycle, when we get to this line, machine state will be evaluated and will then run the code that we write over here, and it will not execute this part of the code. One suggestion for the numbers that we place on the states is to avoid using sequential numbers, because if you wanted to carry out some modifications, you could not simply write over here, let's say, if you wanted to create an intermediate state between 0 and 1, you would need to use another number and maybe lose a sequentiality aspect of your state machine. So typically in automation, many programmers use this strategy. You don't use subsequent numbers, but you use instead of using 1, 2, 3, 4, 5, you may use 10, 20, 30, 40, 50. 10 by 10, because in this way, if you need to carry out a modification and create some intermediate state, here you can simply add state 5 and carry out a transition to state 5, and this will be much more easier to read, easier to modify, and ordered. So I will delete this, and let's say that if sensor A is activated, we will go to the state 10. Okay, so what we did is this transition over here. This transition over here is done by this code. So let's carry out the operations that are done in state 10. In this state, we should simply, first of all, we need to set the command barriers. So let's write over here, command barriers equal to true. So as long as we are in the 10th, in a state equal to 10, this line of code will be kept executing. Okay, so we have carried out this part of the SFC code. Right now we are in the state. Let's also write a comment before the state. Let's call this as we called this one. So the train from above, let's say sensor A state. Okay, then in order to carry out a transition to another state, we could simply evaluate if the sensor B is true. If sensor B, then the machine state should become equal to another state. Let's call this state 20. So with this part of the code, we are actually handling this transition. Okay. Now let's look at this state that we are creating, that is state 20. State 20, here let's write a comment with the name of the state, that is the train from above, that is right now in the sensor, near the sensor B state. Okay, and this should be state 20. So let's write 20 in the column, and over here we shouldn't do anything new, because as we can see, we didn't even do anything new in this part of the code. So we should simply check if the sensor B is equal to false to carry out a new transition. Right now, from this transition, we are getting back to the initial state. So we could simply write machine state equal to 0. Okay, so this is what we are doing, and we have already written this part of this branch of this original state machine that we implemented in the sequential function chart language. Okay, so let's try to build this part of the code. So, starting from the state 0, we could have another transition if instead we have the sensor B condition. In this case, we should move to the machine state, a new machine state that we haven't defined yet. So let's call this machine state equal to 30. And let's add the state over here, 30. That this would be this state over here. So let's write a comment over here to keep track of it. That is drain from below. We are right now on the sensor B. Okay. In this state, as well as we did in the state number 10, we should set the command barriers to true. So let's write command barriers equal to true. And then we should handle transitions from this state. Okay, so we will write if sensor A, that is this transition we are looking into, if sensor A, we should move to another state. And this could be machine state equal to 40. This state over here. So right now let's carry out let's write this other state over here, 40. We should also write again a comment that is drain from below sensor A state. And in this state, as like what we did in state 20, we should simply wait for not sensor A to move on to another state. So if not sensor A, then we should go back to the waiting for train state, that is state 0. Machine state equal to 0. Okay, so over here we implemented our state machine. So let's look at the flow and let's compare it with the SFC code. We start from state 0, where the barriers are raised, just in the same way that we are here. If we read the sensor A, we will move to this state, state 10, where we will raise the barriers. If sensor B is detected, we will move to another state, state 20, that corresponds to this state, where we won't do anything since the barriers are already lowered. And if we read the deactivation of sensor B, we go back to the first state. The same operation is done on the other branch. So if we read sensor B, we will move to this state that is for us state 30 over here, where we will set the command barriers. And if we read sensor A, we move to another state that we call state 40 over here. and in order to get back to the initial state we wait for not sensor A. Yeah, so okay, let's try this. Let's go online and let's open the visualization in a parallel screen. So let's download our program and let's try this, and let's look at the values of variable of the machine state variable. So I will narrow this menu for you over here. I will start. Let's see the state number: 0, 30, 40, because the 0, because the train came from below. 0, 10, 20, 0. This is the sequences that we did. As you can see, the barriers are lowering and raising as we desire, in the same way that we did in the SFC code. So we managed to build a state machine. You can see that maybe for this state machine it is a little bit more complex than the SFC code, that is quite graphical and clear what is happening. But I suggest you to keep practicing at using state machines in structured text, because state machines and structured text are state-of-the-art that are always used in automation, and you can gain a lot more flexibility in structured text, because you can command a change of state wherever you want on any condition. You can create and add complexity without having to create a lot of state transition and states in a graphical diagram. Just like any other graphical language, you may see that it may seem very intuitive and easy to use for simple things, but once you get to complex operations, you may get really big state diagrams that are really hard to read and really hard to structure. So before ending this lesson, I want to look into a few details of the state machines that we just wrote. Especially, I would like to look at these lines of code. This one, this, or line 6, line 18, and line 34. As you can see, there is a little difference between what we did over here in this SFC language and what we did here. As I told you, in the SFC language, the reset operation, reset qualifier of an associated action, will set the variable to false when you enter the state. What we are doing here is setting the variable to false at every PLC cycle in which we are in the 0 state, meaning that this line of code, this action, will be carried out at every PLC cycle, while this one will be only carried out once. The same goes for the line on the state 10 that corresponds to this, and the same goes for this one over here. So this line of code is going to execute to run at each PLC cycle, and for this application it really doesn't matter, because we will keep writing true to this variable that is already true, so we won't see any difference. But in some application you may have someone else, another POU on another part of your code writing this variable, so sometimes you may be setting to true this variable many more times than the ones that you actually need. So we need to carry out a distinction to code that is being executed in the state and code that is being executed in the transition, because over here we could do this simple thing to avoid running these lines of codes at every PLC cycle. So I could simply move this line of code. Let's carry out a cut operation with Ctrl X. I could simply write this here and here. So what is happening in this way? In this way, we are writing this variable to false only once when the transition occurs. Oh, sorry, I meant to do this with true, because over here we are moving to a state that needs to set the variable to true. And I will remove these lines. So what I did is write this variable to true, let's say when we enter state 10 from state 0, and when we enter state 30 from state 0. In this way, this line of code will only be executed once. And as you can see, there will be no line of code setting the barriers, the barriers command in the state 10 and in the state 30. And in the same way, we should carry out this operation in the state that precede this one. So we should, in this transitions, sorry, that precede this one. So we should write over here command barriers equal to false in the transition, in the transition from state 20 to state 0 over here, and in the transition from state 40 to state 0 over here. If we now go online with a download, we will see the program behaving in the same way as before. The barriers are being set, are working from our point of view in the exact same way. The difference is that the code that changes the values of this variable is being executed in the transitions instead of the state. For this kind of application, there is no right way or wrong way to do this. So there is no benefit in using a command in the transition or in the state. But in some applications there may be quite a difference. So you may want to carry out an operation or in the transition or in the state according to the actual need of your applications. So I introduced you to this concept because it may be important in the future to know that there is this difference. So in some videos, in a few videos, we will see some exercises to try to create a state machine, to keep practicing on state machines in either structured text or other languages for different applications. In the last two videos we have seen how to create state machines using the SFC and the ST languages. Right now we will see how to create state machines using ladder diagram. Personally, as I said many times all over the course, I don't use a ladder diagram to create complex code, to write complex code, and I believe that ladder diagram is not a suitable solution for state machines, but I understand that many parts of the world ladder diagram is widely used, so here I will anyhow teach you how to carry out a state machine design using ladder diagram. So let's jump into it and let's create and start from the existing project that we carried out. Let's keep all the programs that we created in the SFC and ST language, and let's add a new program in the ladder diagram language. So I'll write over here PLC_PRG LD, let's call this POU in this way, and the implementation language should be a ladder diagram. Okay, and then in order to execute this POU instead of the one in ST, let's slow double click over here and change the name to PLC underscore PRG underscore LD. Let's build, and we will see this POU becoming gray. So right now the one being executed is the ladder diagram one. So I will place the ST project in this view, so we can create a ladder diagram code based on the existing structured text code. So in structured text we have seen that in order to create a state machine we should have some kind of variable that represents the state that we are into. The same should be done in ladder diagram. So as we did in the structured text language, we should create a machine state variable over here that is a int variable. Okay, now moving on, we should handle this in the same way that we did. So we should separate the code between the states. So check if the state is equal to 0, if the state is equal to 10, and so on. In the structured text we had the case instruction that was really quite useful. Unfortunately, there is no instruction like the case one in the ladder diagram code, so what we should do is simply compare the machine state to the value that represents our state. If the value is equal to the one we are looking for, we should run these operations. So, in order to do this, we should add in our lines of code an equal operator. So let's drag this from the math operator. Let's remove the enable contact, and in order to carry out the operations regarding the state 0, we should simply write over here machine state equal to 0. If machine state is equal to 0, then all the code that we write over here of the operations will be carried out. If it isn't, it will be skipped. So, in order to create the code for this state 0, we should simply follow the flow that we did over here. So, first of all, we should write this part of the code. So we should check if sensor A is true. So we should write right here a contact, the sensor A variable, and if it is true, we should set the command barriers variable. So we should add over here a set coil by clicking here and clicking this button. So we will write command barriers equal to true with this set coil, and we should also set the machine state equal to 10, and this should be done with a move block. So in this point we should add a branch. Let's right click and click on insert branch to create this branch over here, and add a box with ENO over here. This should be a move box, and we should set 10 into the machine state variable. So in this way, with this part of the ladder diagram network, we wrote this code over here. Then we should also write this part. So let's add a new branch over here, and let's carry out more or less the same operations. So we can simply add a contact for sensor B, add a set coil over here by clicking here and clicking this button. Here we'll write the command barriers. Here we will add a new branch for the move operation. Insert branch. We can simply copy and paste Ctrl+C and Ctrl+V this move operation, but over here we should write the state machines, the machine state equal to 30. Okay, so over here we have our first state in a single network. We could also do this in two separate networks. We could use a network to check this part of the code and another network to check this other part of the code. In either way, you should always add as a first condition an equal condition to the state you are looking for. So this is equivalent to carry out this operation in multiple networks. So let's add over here another network for state 10. Let's copy and paste the EQ operation. Let's delete the enable contact, and here we are looking for state 10. So we should compare the machine state with the number 10. And over here we have the code that states that if the sensor B is true, then machine state should become 20. Okay, so over here we will add a contact for sensor B, and in order to do this we will carry out a move operation. So I will simply copy and paste a move block, and over here I should set 20 to the machine state variable. Okay, now let's move on to state 20. So I will create another network. I will copy and paste the EQ operation. I will once again remove the enable contact, and over here we are looking for state 20. So here we are looking for state 20, and we have no actual code as before that is running in the state, so we should simply check if sensor B is now false. In order to do this, we will insert a negated contact over here for the sensor B variable, and if this condition is met, we should do two things. We should set the command variables variable to false and move back to state 0. So we will do two things. We will add over here a reset coil for the command barriers variable, and then we will also add a branch over here to carry out a move operation to set the machine state variable to 0. So click here, right click, insert branch, and I will copy and paste once again a move block. And over here I will be setting the state to 0. Okay, this is good. Then, so we carried out our first three states. So this part of the code, the three branches, this first branch, then we should also create these two states. So you should also have gotten quite familiar with the logic of this state machine that we have already implemented twice in two different languages, and you should know that this branch is quite similar to this one. So for now, in order to I guess you can see where I'm getting with this code. State 10 is very similar to state 30, state 20 is very similar to state 40, so in order to do this in a more simple way, let's simply copy and paste these two states. So I will select them both using, well, first select this one, Ctrl+C, and let's write Ctrl+V by clicking at the end of the networks, at the ladder diagram code without selecting any network. Ctrl+V. Over here I have pasted this code, so let's change this in order to carry out our state 30. We could also have been copying the code in the structured text, but I guessed that it was better to learn everything by writing it by hand. Since we already know the operations, we could simply now modify this state over here to fit the state that we have already written in the state machines we implemented in the structured text language. So over here we are looking for state 30. Our condition for the transition is if sensor A is equal to true, and if sensor A is equal to true, machine state should become equal to 40. Okay. Then once again we should implement state 40. That is quite similar to state 20. So I will copy the code, Ctrl+C, the code belonging to state 20. I will click down here and I will paste it with Ctrl+V. Let's modify it in order to fit our state. This is machine state 40. Right over here we are looking for not sensor A, so let's write this over here. Then we need to reset the barriers command, that is correct, and then we need to set the machine state to 0, and this is already done. So we actually managed to write this code in the ladder diagram language. So before going online, let's have a few remarks about this. It may seem quite simple over here, but as I said, if you have many complex operations, it might get quite tricky. I mean, if you look at this line of code, it is quite clear what is happening. We're looking in state 30. If sensor A is equal to true, we will move to state 40. Okay, but once you get many different conditions and many different operations to carry out, you can see that it becomes quite complex to read. And also this state that is quite simple, it's becoming pretty huge on your screen, and it will get pretty big on a classic automation machine. So what I suggest is to use another language for state machines that is better suited for this type of programming pattern. I suggest you to use structured text, as I've stressed often in these videos, but I mean, you're free to do whatever you want. This is just my personal opinion. And also, SFC is quite powerful as a language because it allows you to implement different actions and code in many different languages and quite easily, and it is quite powerful with the combination of using this and structured text may be quite useful to you. So let's get back to ladder diagram and let's check by going online if the program we wrote is working fine for our train operation. So I will open the visualization in a parallel screen over here, and let's keep looking at the state of the state machine. So over here state is 0, state becomes 10, 20 and 0. And as you can see, the barriers work fine. 0, 10, 20, 0. The barriers work fine. Let's wait for train coming from below. 30, 40, 0. Okay, the code works fine. It is basically the same code that we implemented in the other languages, but right now you've seen that how you can create a state machine using the ladder diagram code, the ladder diagram language. In the next videos we will see some exercises in order to practice with the state machines, and I will carry out an implementation in the structured text language, and I will explain to you my solution, but you're free to use whatever language you prefer. And remember, there is no There is not only one right solution. There are many possibilities as long as the code works and satisfied all the specifics of the application. In this video we will see a first exercise concerning state machines. In the attachment of this lesson you will find two compressed folders, one containing the basic exercise and one containing a solution for the exercise. So I suggest you to download and open the exercise 1 compressed folder and open the project file that you will find. So if you open it, if you have some issue, remember to open the project archive file instead, and inside of the project you will find, as in the other exercise, as a project with a global variable repository, a simulation program that you must not touch, and a visualization to actually see the process. And the overall purpose of this exercise is to control this simulated piston right here. In order to do this, you have a start button and a stop button to have an interface with the user, and you also have two sensors that will tell you where if the piston is at its negative limit or positive limit. The global variables that you can interact with are these ones. You have the following inputs that are the start button, the stop button, the negative limit of the piston and the positive limit of the piston. And the only actuator that you are commanding is this command piston. If this variable is true, the piston will move forward. If the variable is false, it will move backward. So, what I want you to do in this project, in this exercise, is to carry out the following cycle. When you start the program, when you start the machine, when you click start, the piston should carry on a cycle that is about moving forward to the positive limit sensor, wait in this position exactly 1 second, and then go back to the first position. Here I already have an implemented solution, so I will show you what should happen by going online and testing this. Here I go. By pressing play right here. This is the starting position. As you can see, this sensor is lit, and if I press start, the pistons should start moving, reach the sensor, wait a second and come back. Then it should carry on the cycle forever. It should keep moving until I press stop. If I press stop, the piston should come back to the initial position. And another thing is that if I press start and the piston is not at its original position, the piston should not move. The overall machine should react to a start command only if the piston is at its initial position. So, I suggest you to try to implement this on your own. I will provide a solution in the structured text language, but you can carry out this project in whatever language you want. Remember, there is not only one possible solution. There may be a ton of different possible implementation, and they may all be valid. And in this exercises I will show you what I think is the best solution and how I personally did this. I carried out this application. And remember, what you did, what you did is very different from what I did, it does not mean that what you did is wrong. So try this, and in the next video I will discuss and show you my solution. So Right now I will develop my solution for the first exercise concerning the movement of a single piston. I will implement the state machine in structured text. Therefore I will need a variable to indicate the state of my machine. So I will create a variable called machine state, and the type will be a uint type of variable. I will also need a timer, given the fact that we should wait for 1 second both on the negative sensor and on the positive sensor. So we'll create a timer that I will call ton timer, and the type will be ton. Okay, so I should first call my timer right here using F2. We create a call to the ton timer, and I will put it right here, and then I will think on how to interact with it. So right down here I should create my state machine with case machine state off. Okay, and right here I should write my own state machine. So let's start from an initial state, a state 0, that should occur when the machine is not running. This is the state where the machine starts. So machine is not, let's write right here the machine not running. So over here we should tell what should happen in the state. Well, since the machine is not running, we should have the piston not moving, or at least moving backward to its negative position, so command piston should be false. Then we should also deactivate the timer, because right now we don't need it. So in order to deactivate the timer, we could simply set its in variable to false, its in input. So let's evaluate when we need to change state. What are the conditions to change state from this initial state? Well, we should change the state when the machine is starting. So we should surely check the start button. So if start button, then we should move to a different state. For example, machine state equal to 10. Okay, but also we should need some additional condition. For instance, we could add that we don't want the stop button, as we've already seen many times, meaning that if the stop button and the start button are being pressed together, the machine should not start. Okay, and another condition that we said in the previous video is that in order for the machine to start, it needs to be in the negative limit position. So we also need the piston negative limit. Okay, this is good. And when this happens, we should start the piston for it to move forward. So let's write right here command piston equal to true. Okay, so after this, if the machine starts, we will get to the state number 10. Let's say that this state, let's place a comment over here, that the state is a state with the machine running, and right now we are moving forward. And we should continue to move forward until we reach the positive limit of the piston. So if we reach the piston positive limit, then what should we do? We should surely move on to a different state, state 20, let's say. And also we should start the timer. Once we have reached the limit, we should start the timer. So we will write ton timer timer.in equal to true, and let's also place right here the time of the timer. We could write this right here, but since we are using the timer for different operations, placing the setting of the time in the state machine gives us some flexibility if we wanted to modify it. For instance, if we wanted to wait different times in the negative or positive limit sensor positions. So let's write over here turn timer.pt equal to 1 second, t hashtag 1 second. Okay, this is great. So if we reach the positive limit, let's also open right here the visualization so it's clear for all of us what is happening right over here. So we've started the machine, we have reached this point, so the positive limit has been reached, and right now we are waiting for the timer to finish counting. So we should keep the command piston equal to true, and there is no need to write this because it is already equal to true. And when the timer has finished to count 1 second, we should start moving back. So in this state 20, let's say that this is a machine running and we are waiting for the timer end. So right here we should write that when the timer finishes, so when timer.q is true, we should first of all reset the timer. So let's write timer.in equal to false. We should start moving backward, so we should write command piston equal to false, and then move to a different state. Let's say that this is state 30, machine state equal to 30. Okay, that is fine. So we are over here, we finished counting 1 second, and now the piston is moving backwards. So the state number 30 will be the one where the machine is running and we're moving backward. And we should keep moving backward until we reach this sensor. So over here we should have something similar to state 10. We should check if the negative piston, it was a piston negative limit was equal to true, and if it is equal to true we should set again the timer to start and to wait 1 second. So timer.in will be equal to true. Again we will place the time timer.pt equal to 1 second, and then change the state of our machine to another state, let's say 40. Okay, so let's recap what has been done until now. The machine has started, the piston has moved to this position, we have waited for 1 second, and the piston has moved back to the initial position. And now we are waiting for 1 second again. Okay, so let's write this state 40. So machine running, waiting for the timer end. The state 40 should carry out a similar operation to the state 20. We should wait for the timer to end. If timer.q is equal to true, then we should again reset the timer, timer.in equal to false, we should start moving forward because we have waited for 1 second and now we should move forward again. So command piston should become true, sorry. And then we should change state. But since we have already a state where we are moving forward, we could simply jump to state 10. That is the one where we are already moving forward. Okay. So this should in theory work. We have not managed the stop button. So what should happen if the stop button is pressed? It doesn't matter the state where we are in, we should go back to the state 0, where we wait for us to be in the initial position, have the hard button to start again. And look at this, if we go to state 0, we will automatically place the command piston equal to false and the turn timer.in equal to false. So we could write in each one of this state something like this, which could write if stop button, then machine state is equal to 0. So a transition from any state to state 0. But since we should write this in any state of the state machine, we can simply write this outside of the state machine. So this operation will be carried out no matter the state that we are in. If we are in state 0 and the stop button is pressed, we will remain in state 0. If we are in any other state and the stop button is being pressed, we will go back to state 0. So let's now try to go online and test this with the visualization. Let's start the simulation mode, download the application, and right now we can look at the visualization to see what is happening. And we can also look at this machine state and at the code to see how it's working. So, I press play. Right now we are having the piston negative limit. We are in state 0. And if I press the start button, we'll move to state 10 and command piston will become true. Let's see that. I will press start. Yes. We reach this, state 20, state 30, state 40, state 10, 20, 30, and 40. State 20 and 40 are states that are going on only for 1 second because they're the ones that are waiting for the timer to finish, while the 10 and 30 are the ones in which the piston is actually moving. Let's try to press stop in any moment. Okay, piston has stopped and the state has become 0. Let's try this again while the piston is moving forward. Yes, the state becomes 0 again. So, we have seen how to create a simple state machine for a process like this. We have seen how to use timers within state machines, and in the next exercise we'll also have a piston to control, and we will see some additional things about state machines. In this video we will see another exercise regarding state machines in order to keep practicing and know a little bit more about state machines. And This exercise is still based on the movement of a single piston, but there are some differences in the application and in the overall control technique for this piston. So, here is the project that you will find in the attachments. You will have these global variables, and like before, we will, like the previous exercise, you will have a piston negative limit and positive limit, and the start and stop button. The main differences over here is that we have a product presence sensor that will tell us if a product is present right here on the piston. So the task of this piston will be to move this object from the starting position to the end position, and therefore it will need to move only if a product is present. And the other difference is that over here we have two different actuations for the pistons. In the last videos we had only one actuation, and that command was meant to be true if the piston was moving forward and false if the piston was moving backward. Over here we have two commands, meaning that if the first one is true, the piston will move forward. If the second one is true, the piston will move backward. If none of them are true, the piston will stay still. And this was not possible in the previous exercise with a single actuation piston. So right now I will go online and show you what should happen, what should be carried out in this state machine for the control of this single piston. So after having downloaded here the program, here I will show you what happens. If I start the machine, the piston should start moving only if it should start moving when it is at the start position, only if a product is present. As you can see here, this is the overall. Wait a second, I will stop it right here, just a moment. Okay, so I was saying, if the piston starts, you will see that this is the cycle. Here we actually have no waiting times on the positive and negative limits of the system. So the cycle is this one. If the piston is on the negative limit, it should wait for the product sensor, presence sensor to become true, and then start moving, as you can see right now. Then it should get to the positive limit and come back. So it may seem a little bit simpler because we don't have any actual waiting times at the limits, but here is the main difference from the previous exercise. What I want to change is the stop behavior. In the last video we had that the piston, if the stop button was being pressed, the piston should return to its initial position. What I want right now, if I press stop, the piston should simply stop wherever it is, and then if I press start, it should resume the operation that it was doing before, as you can see over here. So this part is also about the management of some kind of memory of the time of the state machine was into when the stop button was being pressed. So this is the main difference that I want you to think about and to try to implement, and in the next video you will see my solution again in the structured text language using state machines. Okay, in this video we will try to create a solution for the exercise that we just presented about the movement of the piston with the product over here. So let's get into it, into the PLC_PRG POU, and let's start to implement our state machine in the structured text language. So first of all, as always, we need a variable to keep track of our machine state, and the type should be an assigned integer. And let's start to create the state machine. So let's first, at the beginning, let's start to implement the overall cycle that we need to carry out without worrying about the stop specifics. So first of all, we will start, as always, in a state 0 where the machine is stopped. So over here I will write a comment, machine not running. And down here, let's see what we need to do. So since the machine is not running, we will have to decide what are the conditions for our machine to start. And in order to start, we should simply need the start button and not the stop button. If the machine, this is what the feedback from the buttons, we should go to a different state. Let's say that we go to the state number 10. Okay, so in the previous videos I presented you some alternatives in whether to control the machine actuators in the states or in the transitions. In this project we will see why it is different, and in this project it is quite better to command the actuators in the states of the machine. So I will write this over here, and later on I will explain you why. So let's set the actuators that we need to set in the state 0. In the state 0, as we said, if the machine is not running, the piston should be stopped. So both of these outputs should be set to false, sorry. Command piston forward should be set to false, and command piston backward should be set to false. Okay, that is good. And over here we should move to another state, state 10. In this state we assume to be in this first position over here, and we should not move until we see a product on the product presence sensor. So in this state, let's call this with a comment, machine is running, but we are waiting for product. And here again we should also have the piston not moving, so we will just copy these two conditions, these two commands, and place them over here. And in order to move to another state, we will need the product presence sensor. Okay, if the product presence sensor, let's write ndif over here. If we read this variable, we should move to another state. Let's say that this state is the machine state, colon equal to 20. Okay, so over here we have actually found a product, so the machine is running, and therefore it should be moving forward, pushing the product. So we will need to change these actual commands in order to move forward. So we will still have the backward command equal to false, but the forward command should be equal to true. So let's copy and paste them over here, and let's write true here. Okay, so in the state we are moving forward, and we are waiting to see if let me open the visualization. We will need to move forward until we hit the positive limit sensor. So if I write, the piston, if piston positive limit, then we should again change state and move to state 30, for instance. We're in state 30, and over here this should be the state in which we are moving backward, because we have just hit this sensor over here. We don't need to wait any time in this exercise, so we will just have a state machine running, moving backward. Okay, so over here we will need to implement the command in order to move the piston backward. That would be the opposite of this one. So command piston forward would be false and command piston backward would be true. Here I will write false and true. And now let's evaluate for how long we should be moving backward. Well, we should be moving backward until we hit again the negative sensor. So if we read the piston negative limit, then we should again change the machine state. But we have carried out a full cycle. We are back to the initial position, and therefore we should go back to state 10, where we wait for a new product. Over here we will write machine state 10. Okay, so it seems like we have implemented this state machine for the overall cycle. We have not implemented still the stop logic, but let's try this by going online and seeing how it behaves. So I will go in the simulation mode. I will log in and download my application on the virtual PLC. I will start the CPU and I will press start, and let's see how it behaves. It seems to work quite fine. Here let's look also at the states. So by looking at the variable, state 20 we are moving forward, state 30 we are moving backward, state 10 we are waiting for the product. So when the machine is running, you will see that this is the sequence 10, 20, 30, 10, 20, 30. Okay, let's go back offline and let's start to implement right now the stop and start mechanics, the stop and start logic. So what should happen when we press the stop button? Well, first of all, we could write a condition over here, stop button. If the stop button is pressed, we will need surely to go to the machine state 0. Okay, but also we will need to keep track of the state in which we were at the moment. So we will need another variable that, for instance, we could call resume machine state, a uint variable, and we could over here say that if we press the stop button, our resume machine state should become equal to the machine state we were into. So what happens is that if we press stop, our machine state will go to 0. But before doing that, the state that we had at the moment will go into this resume machine state. So, in order to do this, to restart, we could simply use this variable in the start condition. So, we should not simply, when we press the start button, we should not simply go to state 10, but we would need to go to the state we were into before pressing the button. So, I will simply write machine state colon equal to resume machine state. Okay, right now there is a problem, and we will see this by going online with a download. If we have not pressed the stop button and we have not been in any state, as you can see, the resume machine state at the first start of the machine will be 0. So, if we press start, the machine state will remain 0. In order to solve this, we could simply write an initialization condition for the resume machine state. For instance, we would like it to be equal to 10 at the first time we start the machine. So we will go to the state 10. Let's again log in with the download. As you can see right now, our resume machine state is equal to 10. And if we press start, the machine starts in a correct way. Okay, this is fine, but there is still some problems in the handling of the stop machine. Here, let's try to press the stop button. You can see that I pressed the stop button, we were in state 30, but right now the resume machine state has become equal to 0. This is due to the fact that I have not pressed the stop button for only a cycle, but I may have kept it pressed for more than a PLC cycle. So what happens over here, I press now the stop button, and the resume machine state gets overwritten by 0, because this is the state in which the machine is right now. So we should also try to avoid this, and right now if I press start, the machine won't start again. So we should avoid this. We should always guarantee that our resume machine state will never get equal to 0. And in order to do this, we may carry out the stop operations only if we are not stopped already, meaning that we could add an end condition over here saying that we will need to stop the machine if the stop button is being pressed and the machine state is not equal to 0. In this way, we will never overwrite our resume machine state to a value that is 0. Let's try this by going online and carrying out a download. Let's start the PLC, and right now we have the resume machine state equal to 10, so we'll press start. The machine starts correctly. So let's stop this when the machine is again in state 10. Sorry, in state 20. Let's try this. I stop the machine, and as you can see, the resume machine state is equal to 20. And if I press stop again, you can see that the resume machine state is not being overwritten because this condition over here is missing. So, right now, if I press start again, the state machine will get back to state 20. And it will resume the operation. Let's try to stop the machine over here. My resume machine state becomes 30. I press start, and it starts. This is great, this is working just as we wanted it to, and this is a good solution for this exercise. I will now stop in state 10, start. It worked flawlessly. So right now I will make a few comments on why we built this machine with the actions, with the commands in the state, instead of doing them in the transition. Well, we did this because we wanted the activation or deactivation of the movement of the piston to be connected to the state. And this is actually due to the fact that we are resuming the state from the zero state. We may go to any state, meaning that if we are in state 0, we may go into state 10, into state 20, or to state 30. So from state 10 we could have 3 different conditions, 3 different transitions. So if we wanted to do this, carry out this operation by having the commands for the piston in the transition, we would have needed to do something like this, to write something like, if the resume machine state is equal to 10, then we should have set the command pistons according the command pistons like in the way we needed for that state, by doing exactly this. Sorry, here. If instead the command piston was equal to 20, we should have needed to say that the actual piston commands were meant to be different, and so on. And we could have simply removed all of this condition, all of these commands, actions over here. But in this way, it is much more cleaner, and you can see that if we move to a state, we have a movement condition associated with the state that will overwrite the current movement no matter what it was. So it doesn't matter if we get to state 30 from the state 20, or if we get there from state 0. In any case, we will overwrite the movement conditions that were in place with these new ones. So this is an implementation of a state machine where we needed to actually control the piston regarding to the state in which the state machine is into. And another thing that was a little bit tricky was the handling of this resume operation. We saw this exercise that was quite different from the first one in many things, and in the next exercise we will still need to look at this exercise for the state machine, and we will look at the modularity of a PLC program. In this lesson we will see how functions work in codesys, how to create them, how to implement their use within other POUs, and in order to do this we will create a function to carry out a task that we already discussed, which is the scaling of analog signals that we discussed at the beginning of the course. So we will try to create a function to carry out this process in the easiest and the most simple way for a user. So let's create a new project. So let's call this, for instance, a function analog scaling, and let's create a standard project. Let's press OK. Right now we don't care about the language of the POU because we are gonna delete this for now. So for now I will delete this, then I will look into it again later on. So let's try to create a function to carry out the calculation for the analog scaling operation. So let's create here a function. Let's call this fc underscore analog scaling, and over here let's select as the implementation language est language. Okay, sorry, you should always specify a return value for the function, and in this case we will need, let's say we'll specify everything as a long real variable, because all the numbers may be floating point. So let's add the function, and here this is what you will see over here. It is a simple POU, and it has the same aspects of programs, function blocks, and so on. But over here you will see a colon and a type. This is the type of the return value of the function, meaning the value that will be returned by its calculation. So let's remember that a function is an entity without memory, meaning that we will use some variables, maybe have some internal variables, but all the code will be run within a PLC cycle, and then the variables won't exist anymore. So you cannot, for instance, call a function many times and expect for the value of the variables in it to be kept. Every time a function is called, the variable take their initial value, and when the function returns from its execution, those variables then are not accessible anymore. So let's carry out the operation of the analog scaling and a signal, how to scale an analog signal. So as you recall, we saw this formula that I will show you over here, and this is the formula to carry out the scaling of the scaling operation, which is like a simple algebraic calculation. So our output of the function will actually be this v2 variable over here. So in order to carry out this calculation, we need some variables. We need to know v1, meaning the input value for the scaling process. We need to know the minimum of the input and the maximum of the input that are allowed. Then we also should know the maximum of the output and the minimum of the output. So let's try to set these 5 input variables. Let's write them over here. Let's say that we need the input value as a long real, the input minimum again as a long real, the input maximum, and we also need the output minimum as long real and the output maximum. Here we go. Okay, so here we have these variables that we can access and use for our function, and let's see how are we gonna compute this actual value. The value that we will return will be set onto the actual name of the variable. So to carry out this computation, we should write fc analog scaling colon equal to something that returns the result of this calculation. So let's try to put this together in a simple way. So let's write this equation in a sequential way. So first we have v1 minus minimum 1, that in our code should be, let's put this into brackets, and this should be the input value, minus the input minimum. That is just saying v1 minus minimum 1. All this is divided by maximum 1 minus minimum 1. So let's divide this and open a set of brackets and carry out this subtraction. Input max minus input min. And let's now here all of this is multiplied by this difference, maximum 2 minus minimum 2. So here we write times output max. Let's remember input is our variable 1 and output is our variable 2. So minus output min. And again for the last one, plus minimum 2. So over here plus output min, semicolon. Okay, so this should actually work and it will compute the correct number. Let's also carry out some additional check, because if you enter some wrong values you may run into some problems, especially here, because you can see that we are dividing by some numbers, and as you may or may not already know, a division by 0 is something that a computer and a PLC doesn't like. It may carry out lead to exceptions and errors in the execution of code. So here we have that if input max is equal to input min, this difference over here is actually equal to 0. So we will be dividing by 0. So we could carry out a check to see if the input values of the functions are correct, are acceptable for our scaling operation. So let's create over here a variable, an output variable, here by writing var underscore output, and let's call this output variable error, and this error is a Boolean variable. Okay, this Boolean variable should be presented with the actual conditions that lead our function to errors. For instance, we could write over here error is equal to input max being equal to input min. In this way, what we are doing is that this variable will be true if they are equal and will be false if they are not equal. Okay, first of all, let's now see what are the main issues that tell us if the user has entered some wrong values in the input of this function. Well, first of all, let's make this statement more general, because what you actually don't want is also the minimum being bigger than the maximum. This has no sense, and therefore our function should tell the user that this is wrong. So here we could say, since we don't want the minimum being equal to the maximum and we don't want it to be bigger than the maximum, we could say that our condition may be the input min bigger, greater or equal than the maximum. This is a wrong condition that will lead us to an error. So errors should be true if this condition is happening. Let's write. Also, we may have additional conditions, so let's write over here an or statement with other conditions. Well, another condition may be the same on the output. We don't want a wrong scale, so let's write output min greater or equal than the output max. This is wrong as well, and we don't want this. And another thing that we could check, is if this input value is actually in the range of the input min and the input max. So we could issue an error if the input value is lower than the minimum or bigger than the maximum. So by writing this, input value lower than input min, or input value bigger than input max, sorry. Okay, so over here we have 4 conditions. If any one of this is true, our error will become true. And we actually don't want to execute this line of code. And in order to not carry out this operation, we could simply say here, let's say that if not error, then we will execute this. Otherwise, let's simply set this value to 0. Else, FC analog scaling is equal to 0. In either way, the output error will be set to this OR condition, and if an error is present, the user that is using this function will see it. So let's test this function out. So let's create right now a POU, a program, and let's call this again, that's PLC_PRG, and for instance let's implement this in a function block diagram in order to be able to see more easily the values of the function. For this, the function block diagram is quite useful. So let's define in our let's first try to call this function. So in order to do this, let's insert over here a box, and the name of the box over here will be the name of the function, FC analog scaling. Okay, we need to specify all these values and also this one, so I will insert an assignment over here by dragging it over here. Okay, so we need some variables we need to put some variables over here. So let's create some local variables for the POU in order to do this. Let's say an input value, let's say input scaling value, a long real variable, input scaling minimum, in order to have some different names. It is not necessary, but I wanted to not create any confusion in you. Input maximum, long real, output scaling minimum, a long real, and output scaling maximum, long real. And then we should also specify an output, so the output scaling value, that is actually the output of the function, long real. And then let's also add an error of the scaling, and this should be a Boolean variable. Okay, so let's you should write all these variable definitions, and let's copy and paste all these values in the function. Copy and paste, copy and paste. You can see that calling a function is not much more different from calling a function block. The difference is that this object has no memory, so it will carry out some procedure, some code using its inputs, and will return some values and die over there. So I will copy and paste all these variables in the correct place. Okay, so right now let's try to go online a simulation and see what happens. login with a download. Oh, sorry, of course, I forgot to schedule this program, so it won't run. You should add it in the main task. So I will write here, over here, PLC_PRG. Okay. Let's now go online with download. Okay. So as soon as I start the program, you will see that the function is an error. Why is this happening? Because all our variables are 0, and many of the conditions that we specified are actually happening. Input minimum is bigger or equal than input max. Output minimum is bigger or equal than output max. So actually some conditions are triggering an error. So let's try to create a scaling operation with the values, for instance, of the temperature sensor that I specified in the example in the theoretical lesson. So what I said was, let's assume to have a temperature sensor that measures temperature in degrees ranging from 10, I said, to 50 degrees. So here I will write the minimum of the output, that is 10, and the maximum of the output, that is 50. Okay, I should also write the inputs, and I said that the voltage coming from the sensor was ranging from 0 to 10 volts. So I write 10 in the outputs and leave 0 in the, 10 in the input maximum and leave 0 in the input minimum. And the value that we were reading at the time was 7 volts. So right now let's try to do this. Let's try to set this value and see what is the return value of the function, and let's see also if the error scaling works. Okay, as you can see right over here, the value is actually 38. That was the value that we came up in the theoretical lesson. And as you can see right now, the error scaling is false, and it is not returning this value, an error warning, an error alarm over here. So everything is going okay. So in your real application, you may attach this to the actual value that you're reading from the sensor in order to carry out a scaling operation. And in your program, you will be able to do this by copying and pasting this and using this for any variable that you need, any sensor that you need. So here let's try also to carry out the inverse operation. So let's try to scale this 38 degrees into a voltage. So here we will have 38 as an input scaling value. Here we will have the temperature range that was ranging from 10 to 50. Over here, 10 to 50. And here we had our scaling of the voltage from 0 to 10. And in doing this, we should read over here the value of the voltage that we expect. And by pressing Ctrl F7, as you can see, the output is 7 volts. That was what we at first entered in this value. So as you can see, it works both ways. You can also carry out an inverse scaling operation. So this is how you build, how you create functions, and as you see, this is how you use them in the function block diagram. Using them in structured text is done in the same way that we saw for handling function blocks, and the same goes for ladder diagrams, CFC, and so on. So these functions may be quite useful if you have some operations that you carry out more than once within a program. So this is how you do, and they are of course useful and can be used only if the operation will fit and is able to fit within a single PLC cycle. If it is something that needs time to carry out some operation, or if it is something that needs some memory, you should instead create some function blocks, and in the next video we will see how to create function blocks and how they are useful in an exercise that we will carry out together. In this video we will see a last exercise that we will carry out together, and this exercise is about modularity and the development of function blocks. So, as you can see right here, we have a visualization where the setup is quite similar to the one of the previous exercise. But instead of having just one piston, we have 5 pistons that should move independently and carry on their cycle on their own. So, we have 1, 2, 3, 4, 5 pistons, the same start and stop button that will start and stop the pistons all together, and the main difference between these 5 pistons is that their product generation times are different, so they will not move together for all the cycles. So they are not synchronous at all. They should be independent pistons. So if we look into the global variables of this project, we will see that we have the start and stop button, and then we have the variables that we had in the previous exercise for the piston 5 times. So we'll have a forward and backward command for each piston, a positive and negative limit for each piston, and a product presence sensor for each piston. So in order to carry out the control of these pistons, we could simply copy and paste the code that we did for the previous exercises. We could paste it 5 times with just modifying some little things in order to index the correct global variables. Well, this would work, but it will create many lines of code. It will be not structured, it will be hard to read, and it is very I suggest you not to use a strategy like this, because in the IC programming languages we have some tools that are quite useful for modularity, meaning for some objects that are replicated many times in our code. We saw the functions in one of the last videos, and right now we will see the function blocks. So let's start by looking at the code that we did for the previous exercise. So the concept on doing this is not to copy that code directly into our program, but instead we should create a function block with a very similar code to the one we did for the previous exercise, and in that function block will be instantiated 5 times in our program, 1 for each piston. So let's start by doing this. Let's right click on application and add a new POU, and this POU should be a function block. The implementation for us should be the structured text, and this function block should be called, let's say, FB_piston add. Okay, so in order to handle the piston, we should decide which are the input and output variables for this FB. So, recalling what we did in the exercise about the single piston, we needed to have as the inputs a piston negative limit. That should be a Boolean type of variable. A piston positive limit, again a Boolean variable. A product presence sensor, and then as the output we would need the commands to move forward and backward the piston. So the command piston forward, that would be again a Boolean variable. We will then need also the command piston backward as a Boolean variable. And then, if you recall, we also used the a variable for the state of the piston. So in this implementation we should call this piston state. That should be a uint variable, and a variable to memorize which was the state in which the functioning of the piston was stopped. This was useful to resume the operation of the piston. So let's write this as a resume piston state, a uint variable. Okay, so right now we could simply copy and paste the code that we did for our previous exercise, and we should place this over here in the implementation of this FB. I will copy and paste it from the exercise. If you do not have that exercise, you can download the solution in the exercise 2 video, or you can simply stop this video for a while and take your time to copy this code over here. You could stop and copy it manually. So, as you can see, we need to carry out some modifications because we see some variables underlined in red because they had a different name. In particular, we have now the piston state that in the previous video was a machine state. So I will replace this by double-clicking, copying the piston state and double-clicking over here, Ctrl V, over here again Ctrl V, and so on. I will replace all the names of the variables of the machine state, and I will do the same for the resume piston state. I will copy this and I will paste this wherever we use the resume piston state. Okay, so and in order to be correct, let's also change the comments where we had machine. Right now we should have piston. Okay. So moving on, there is also another modification that I would like to carry out. As you can see over here, we are using the start button and the stop button of the project, meaning that these two variables are not defined within the FB, but are our global variables that we have over here. And this may be working in this project, but a general line for the development of FBs or functions should be to never use global variables for these kinds of operations, because you want your function block to be able to work in any project that you imported where you import it. So if we move this function block in another project where we have the same kind of piston, but we don't have those kind of variables, the function block will not work. So let's also add over here an enable input, a Boolean input that should be commanded from outside of the piston function block and should tell us if the piston is enabled or not. So in order to use this enable Boolean variable, Boolean input, we should replace this condition with the enable input, and then we should simply add over here, instead of the stop button, we could write if not enable. So in this way, our function block is not linked to any global variables, and therefore it should work in any project, with no regard of the global variables that are defined there. So, okay, right now we have this piston function block. If we build our project, you will see that we will encounter no errors, but of course this FB is gray because it is not being used anywhere. So in order to carry on with this exercise, we should simply go into the PLC PRG that right now is empty, and we should start using these FBs. So over here I will instantiate an FB piston 1, and the type of this variable will be the actual FB piston that we have just created, and I will do this 5 times. So I will simply copy and paste this line 5 times, and I will modify this by saying 1, 2, 3, 4, and 5. Okay, so over here we have these 5 function blocks defined within our program. So the memory is allocated, but right now we are not calling these function blocks. So in order to call them, we could simply go into the implementation code, press F2 and go into the input assistant of codesys and write the FB piston 1, for instance. And over here we have the implementation of our piston 1 function block. We could simply add the variables we need over here. Right now I will suggest you to do something different, and this will be done by using the actions. So we saw in one of the first lessons what actions are. They are simply a repository for code that we want to create within a POU to store some code that will be run. And the peculiarity of using actions is that you can create actions in any of the IEC language within a POU that is in another language. And for instance, here we will create an action that we will call, let's call this FB call underscore action, and we will implement this action in FBD, in function block diagram. And this will be quite useful to actually see visually the call of our function blocks. So if right now I build our program, our FB call action is not being called anywhere in our program. So in order to run the code that we have in this section, we just simply need to write the name of the action with open and closed brackets followed by a semicolon. So in this way, when this line of code is called, it will simply start executing all the code that we put right here. And right here we could simply place our piston calls. So I will insert over here a box, and I will say that this box is the FB piston 1. So over here we have our FB piston, and this line of code will call actually the code of our FB piston for the first implementation, first instance of the piston. So right now I will remove the question marks, and over here I will add an assignment because we also need to assign this output. Okay, so in order to do this, we will simply need to fill our function block inputs and outputs according to the global variables that we have. So we will need to carry out a quite mechanical, quite repetitive operation. So I will simply need to copy and paste the global variables from here to the input and output of the FB. So over here I will need the piston effective limit 1 because we are controlling the piston 1, the positive limit over here and the presence sensor over here. Then on the outputs I will need to have the command piston 1 forward and command piston 1 backward. Okay, so this is fine, we did this, and also we don't have any variable to place over here. So we could simply go into our PLC PRG program and define a variable that we will call, for instance, enable pistons. That should be a Boolean variable. And we could simply place this over here, and then we should write over here some logic to handle the values of this enable piston variable. So this enable piston variable that is in a program should react actually to the values of our start and stop buttons. So we could simply say that if we press the start button and not the stop button, then our enable pistons should become true, and instead if the stop button is being pressed, so we will write an else if over here, stop button, then enable pistons should become false. Okay, this is good. I will go back over here, and right now we have the implementation of one piston. So let's try to go online, and right now we are just managing our first piston, and let's see if this works. Let's open the visualization over here so we can actually see. Let's run the PLC. Okay, as you can see, over here we see the values of the inputs of the first piston, and right now we have the piston negative limit equal to true, as we are in the initial position, and the product presence sensor equal to true. And the outputs are both false, because we are not issuing any command. So I will simply right now start the operation, and let's see if the first piston moves. The piston doesn't move because we forgot to do one thing. In the FB piston, as you recall, we needed to initialize this variable to 10, and this is something that we forgot, so I will go offline over here and write colon equal to 10, because otherwise, if you recall what we did in the second exercise, this was also down there, so I will carry out the download again. And right now we will see if the piston starts moving. So let's go back into this call to monitor closely the values of the variables. Let's start the PLC, and over here I will press start, and as you can see, the piston is moving. So our PLC underscore PRG is calling this function block that is totally handling the control of the piston, and the values of the inputs are coming from the global variables, and the values of the outputs are going to the global variables. Okay, this is fine, so we should start to implement this for all the other pistons. So we can simply go over here and copy and paste this line 5 times. 2, 3, 4, and 5. So, and right now we need to modify these lines in order to be able to differentiate, to use this for different pistons. So right now we will carry out some repetitive operation. This will be piston 2, and we will change the names of the variables here. Now this will be, all the limits will be referred to piston 2. You can also do this on your own and maybe skip ahead in the video, but I will do this with you if you want. Piston 2, Here we have piston 3 that will handle the variables coming from piston 3. As you can see, the enable pistons will remain the same variable for all the FBs. So in this way you will have all the pistons being enabled and disabled together. Here I will have piston 4, piston negative limit 1 will become 4, and again we will have 4. Here again, and we're almost done. We just need to, to handle the last one. This will be piston 5, and piston 5. Okay, this is the last variable, and we should be done for this implementation. Let's double check to see if everything is referred to the correct piston, and all of these pistons refer to the same type of function block, to the same, let's say, class, to the same code, but they will run independently. Each one will refer to its own internal variables, and we actually made 5 copies of the same object that will work independently. So let's now go online again and let's test if this works fine. Let's carry out a download. I will open the visualization as before in parallel. I will stretch the windows so we can see all the values of the variable. I will simply start. This may be a little small for you. I will zoom it in a little bit. Okay, so we are over here. We are stopped. As we can see, the enable pistons is false. So let's now press the start button and see what happens. Okay, all the pistons are moving together. It may seem that they are synchronous, but right now we will see that the product generation times are different for each piston. So they are actually moving independently. Each one is reacting to the values of its inputs and it's acting on its own outputs. So we just wrote the code for the control of a piston once, and we implemented this to control actually 5 different pistons. This is the core of modularity within a PLC. It is a very important concept and you should know about it, because typically in automation you may have to deal with many components being repeated or repeatedly used within a machine control. So modularity is the key to create reusable code. That is a very important aspect in PLC programming, and to actually handle all the code in a modular structure. And as you can see, if the piston works correctly, if the piston function block is implemented correctly, it will be implemented correctly for all 5 of them. And you will be sure that they will be working in the same way. Okay, this was all for this video. This is very important, and I hope that you learned how to create function blocks, how to use them, how to call them, and we also use this feature of using actions, and I really like to use FBD for this purpose, because Many times it happens that you will need to call some function blocks in your code and just call them without any interconnection. And personally, I really like to call them in an FBD action because it is much easier to see what is actually happening and more than in structured text. So if you want, you can always create an FBD action and write there the call of your function blocks that will be handled maybe from the outside, as over here we are handling this enable pistons variable. So this is all for this video. I hope that you liked this exercise. Congratulations on completing this course on PLC programming with codesys. In this course, we learned what a PLC is and how it works. We learned the features and definitions of the IEC 611313 standard. We learned the PLC programming languages and the codesys environment. At this point, you should have the necessary tools to write your own first PLC programs independently and to be able to create different applications for automation. I recommend to keep practicing with applications and exercises to become familiar with the provided concepts and tools. If you have any question or suggestion regarding this course or possible future courses, do not hesitate to contact me via Udemy. I am available, I appreciate any kind of feedback, and I want this course to be as effective and targeted as possible. Thank you very much for participating. See you next time.